Hi there, I'm Adam Dalla. Over the course of the next however long this video ends up being, I'm going to be explaining the mathematics behind neural networks, specifically artificial neural networks, feed-forward neural network, whatever you want to call them, the standard neural network, and specifically focusing on backpropagation and how the mathematics and calculus works in backpropagation. So I just want to cover a few big picture introductory prerequisite things, and then we'll jump right into that. So let's get to it. Transition. Woo. Alright, let's talk about the prerequisites for this lecture. Very important. So let's start from the beginning. Something really to stress is this is not an introduction. If you're looking for an introduction to neural networks and how they work and kind of the high-level explanation, there's plenty of amazing resources for that sort of thing. I'd recommend Andrew Ng's course, but there's just hundreds of videos. 3 Blue 1 Brown has a great video series, but this is not an introduction. This is for people who want to know a little bit more about the mathematics that's happening beneath the surface. Second, all is needed is basic linear algebra, nothing too complex, no matrix factorizations or eigenvector, eigenvalue stuff. It's just transposing matrix, multiplying matrices, adding matrices, dot products, vectors, kind of the simple, nothing too complex. And then multivariable calculus is probably the majority of what this is going to be. That's kind of the basis for all of backpropagation. You should be pretty familiar and kind of comfortable with single variable calculus, and you should be familiar in some sense with multivariable calculus, specifically differential calculus. There's not going to be any integral calculus in this video, and then as well as you should at least kind of know what Jacobians and gradients are and how they work in differential functions in multivariable calculus, and just kind of be familiar with how that works, and probably have derived a few equations, and yeah. And then base ML knowledge. I'm trying to keep this short because I've done already a take of this and I talk way too much. So base ML knowledge, just a base ML knowledge of what a cost function is, gradient descent, in general just knowing how machines learn. So those are the prerequisites. If you're still here, we're going to have a lot of fun, so we're going to jump right into the agenda and what we're going to cover next. So, transition. Boom. Alright, so this is going to be the agenda for what we're going to be covering in this lecture. This is obviously a very abbreviated version. We're going to be covering much more than this, but this is just so you can kind of get a good idea of what's going to be happening. So first we'll be starting with a big picture of neural networks and backpropagation. Of course, this is not an introductory course, but just kind of talking about what the big goals are here and what we're trying to do with backpropagation, so we can keep that in mind when we're talking about the more, nitty-gritty. We always have an idea of what we're trying to do. Next, we're going to be talking about just a quick review in multivariable calculus and differential calculus, talking about Jacobians and gradients and how they come about from just trying to derive functions with multiple variables. And just a note, I'll be saying matrix calculus and multivariable calculus sort of interchangeably in this lecture. Anyways, so next we have a view. I'm going to just kind of explore this idea of seeing a single neuron in a neural network as a function that takes in a scalar and takes in a vector and outputs a scalar. So that's kind of an important idea. And then next we're going to be talking about Jacobians and how they work out in neural networks. So we're going to be looking at a very simple neural network and seeing how that works. Next we're going to be seeing how those gradients calculated in this help us optimize and use gradient descent. I'll be talking quickly about stochastic gradient descent and a few other things, but we're not going to be spending too much time. And then here's the big monster. We're going to be talking a lot about backpropagation. Firstly, just with scalars and vectors, and kind of keeping it with notation, but then we're going to be jumping into what those actual derivations and matrices and Jacobians look like when we're dealing with big time backpropagation. And I just put this here so I don't forget. All sources that I'll be talking about in this video will be linked in the description, and then there's a few important ones that I'll mention, but in general, yeah, lots of different places. Anyways, so let's just jump right into it. First off, we're going to have a big picture and talking about some notation, and yeah, alright, see you in the next clip. Alright, so just some quick stuff to get out of the way. We're going to be just quickly talking about the notation we're going to be using. Most of it's pretty standard, so if you're in machine learning already, you probably get most of this, but just a quick review, and there's going to be much more notation coming on later, but I'll explain that when we get to it. This is just kind of the important preliminary stuff. So M is going to be the size of our training set, so it's going to be the amount of training examples we have. N is going to be the amount of input variables we have, so each training example will have N different input variables. We'll often say x1, x2, and then xn, right, to each one of these is one of our variables, of our input variables. Next, L, capital L, is the amount of layers in our neural network. Next, lowercase l is regarding a specific layer, so it's sometimes in the superscript or subscript of another term. For example, weights. So this is the weights of layer L. It's a bit complicated. I'm kind of to think about the notation here, but W with superscript L, with L is the layer the weights are going into. So you can think about it here. So if this was layer 1 and this was layer 2, and these weights would have the superscript 2 because they're going into layer 2. Similarly, the bias for layer L is going to be, if the bias was here, it'd be BE2 because this is the second layer. Lastly, X with subscript I to denote which variable it is a single input variable. And again, each of our training examples has one of each input variable we have. So that's all we need to know for notation, so we'll continue on. Alright. Alright, let's get into the real stuff. So this is the big picture, and these are just a few things that we want to keep in mind when we're going through the nitty-gritty in the math. So the first thing we want to think about is neural networks as functions. A lot of people think of them like this, but it's important to keep in mind that a neural network is just a big fancy function made up of a lot of little functions, and all the parameters to this function are the weights and the biases, however many that may be, and the inputs to this function is usually vector of all the variables of one training example. So you have this beginning of a neural network here, like this, and these all go to whatever layer, and then the input is some x1, x2, x3, x4, blah 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 for xn. And then the output can be a lot of different things depending on the neural network. Often, if you're thinking of something like image classification, it might be a vector of probabilities, and then you choose the biggest probability for your classification, or something like that. But the output is often a scalar, or a decision, or a yes or a no, or something like that. So it's basically turning these raw numbers into something understandable. Secondly, just to erase that, make some space. Secondly, we want to think of this as just one big calculus problem. That's really all it is. We're trying to minimize the cost function. So you might see Terminator or something like that. All those are just calculus. Really just one big minimization problem in calculus. You're trying to take the cost and trying to minimize that. So you're doing that through a very, very complicated, huge chain rule operation, pretty much, with respect to however many of these parameters you may have. As I was saying, this is all about the cost function and minimizing that cost function. More specifically, it's all about finding the derivative of the cost function with respect to every single weight and bias. So that's basically, just think about it like this. So if you have a function with, say, 1,000 parameters, 1,000 weights and biases, to best figure out how to lower that cost function, per se, so get down here, is to find out how much each weight and bias contributes to the cost. So then you can appropriately add or subtract the different weights to make sure you're finding your optimal algorithm. So basically that's why we're trying to do all of this, and that's why the entire goal of backpropagation is to find the derivative of the cost with respect to every different weight and bias. So basically how the cost changes when we change a weight or a bias in our algorithm, and this can help us kind of tweak them, kind of learn about how each one impacts the final cost, and yeah. Lastly, just to keep in mind how exciting this all is, really deep learning has become so much bigger in just the past 10 years, and although this stuff was actually invented in the 1960s and 70s, backpropagation, as it was thought, was actually new. It was 1986. But anyways, it's some older math, but this is being applied in very novel ways. And it's not a super big stretch from this to the cutting edge. So it's quite interesting, and I hope you'll be enthusiastic about all the math we're learning. So yeah, so after that I'll just hop right into the real math. So yeah, see you there. Alright, so let's just jump right in with some matrix calculus, starting with gradients, which is how we display the partial derivatives of a function that takes something from being a vector to being a scalar. So let's see what I mean by that. Let's use an example. So let's say f of xy, so that's two input variables, equals x squared, plus cosine of y. It's getting a bit close there. Perfect. So let's take the partial derivatives. So with respect to both of the variables. So this, and then x is going to be 2x, and then we're going to do this with respect to y, which is going to be minus sine y. So those are two partial derivatives. That wasn't too tough. So let's explore what I meant by taking something from being a vector to a scalar. So let's take this vector, let's take this function, and so this might not look like a vector, but we can display it as one. So we can say x and y, so that can be our input. And then we put it through f of xy, which I guess you can see is a vector function, and then it returns some sort of scalar. So let's just, to make it concrete, let's put some numbers in there. So let's say x equals 2 and y equals 0. So let's plug those in there, so that would be 2 and 0 instead. Right, so 2 squared is going to be 4, and then cosine of 0 is going to be 1. So we're going to add that, so it would be 4 plus 1. It's going to kind of look like an S, but it's going to be 5 now. So that's our vector, which is an R2, to our scalar, which is an R1, as says here. Right, so that's going to be that kind of function. Anyways, so a gradient. So a gradient is how we can display the partial derivatives of this function, or any function like this that takes a vector to a scalar. So a gradient, it might sound kind of complicated, but all it is just a vector of the partial derivative. So in this case, in any case, it'd be this and this. So it'd be the partial derivative with respect to x and the partial derivative with respect to y. So that would go on for how many, so if you had 1,000 input variables, there'd be 1,000 items in this vector with respect to each input variable. But now we just have 2. So of course in our case, this gradient would equal 2x and negative sine of y. So this would be described as the gradient of f of xy. And just some notation for gradients that we're going to be using in this. That's pretty common. So a gradient is given by this upside down triangle sign. I think it's a delta, but don't. Is it a delta? I put it, I think. Yeah, oh no, it's a nabla. Sorry. So nabla. Right? So we have this upside down triangle. Just call it an upside down triangle. We don't have time for this elitism. And then we have an upside down triangle. And then we have the name of this function, so f. And then sometimes you can do x, y. So that's the gradient of f. So this is the sign for a gradient. So whenever you see this, think of something that looks like this, partial derivatives. All right, so we got that down. So that's a gradient. Next, let's talk about Jacobians. So Jacobians, instead of taking a vector to a scalar, take a vector to a vector that might be of same or different shape. So, so vectors. Alright, so, Jacobians. So let's take an example again. So let's take another function that takes in 2 variables, x and y, but instead of returning a scalar, let's make them return a vector. So let's make, what are these 2 functions? What do you want them to be? Maybe 2x plus y to the power of 3, and then maybe e to the power of y plus 13. Let's make that a negative 13. Negative 13x. So here we go. That's our function that gives in an R2 input and a R2 output. So, taking the partial derivatives to this is a little more complicated, because now we have more than one function technically. So how we're going to break this up is we're going to make it into basically two scalar functions. So we're going to say f1 is equal to the first row, and f2 is equal to the second row. Not too hard. So now we can just take the partial derivatives of each of these functions with respect to the variables, just like we did before, but now we're kind of doing them separately. So let's take this first function for us, f1. So let's make a space for f1. So let's take the derivative of f1 with respect to x. So all our input variables. So that's going to be equal to, so let's look at our first function f1, look at x, that's going to be a 2, so it's going to be a 2. Let's take f1, and then let's take it with respect to y, the other variable, and that's going to be y, so we're going to use the power rule, equals 3y squared. So now we have these two derivatives, but then we also have this second function here, f2. Let's make a space for that. So now we have f2 with respect to x, and we're going to take that, so ey, so actually no, for some reason I switched them around, probably don't want to switch them around, but whatever, so we're going to have 13, so it's going to be negative 13, and then we're going to have f2 again, and with respect to y, so that's going to be e to the power of y. Awesome. So now we have these 4 partial derivatives, and see that now that we have 2 and 2, we're going to have 4 partial derivatives that we have to calculate. So we already see that we're getting more and more partial derivatives. But, similar to the gradient, how we're going to calculate this Jacobian is going to be how we kind of assemble these partial derivatives. So let's make the Jacobian here. So all we do is, this is actually a very similar arrangement to the Jacobian. So before we put, all we did is we put the gradient, right? So that was the x and y with regards to functions, that would be with respect to x and with respect to y. So now we have 4, so now what do we do here? So what we do is we have 2 lines in this. So these are going to be the derivatives with respect to the first function, and these are the ones going to be with respect to the second function. And obviously, with the more lines our output has, the more lines this is going to have. So one way you can think about it is that each of these lines are going to have the derivatives with respect to x and y. So it would be the first function with respect to x, first function with respect to y, second function with respect to x, and second function with respect to y. So you can almost think of it as each line of this Jacobian is a gradient of each function. So this would be the gradient of f1, and this would be the gradient of f2. And technically it's the transpose of those gradients, because before we had those vertical gradients, now they're horizontal. So that's not too hard. But let's actually fill this in just for completion. So just from here, that would be you get it. I'm just going to concentrate on not screwing this up. So it's going to be f1, and then with respect to y, and then f2 with respect to x, and then f2 with respect to x. So it's going to be a 2 by 2 Jacobian, and then the rows, as I said, are the functions, and these are the variables, the columns are the variables. So let's just fill those in for them. So our Jacobian is going to look like 2, and then 3y squared, and then our bottom row would be negative 13, and then e to the power of y. So that's our Jacobian for this function. Alright, so hopefully you got that. Alright, so next up let's talk about Jacobians, which are basically how we display the partial derivatives of a function that takes a vector to another vector. So let's do an example again. So let's say f of xy, this also takes in 2 variables, but this time we got a vector function that returns a vector. So what do we want this to be? And what do you say, maybe something interesting. 2x minus y to the power of 3, and maybe e to the power of x plus maybe negative 13 y. So now we have a R2 scale vector going to an R2 vector. These can be different. You could have an R3 vector and have another thing, but we're going with an R2 vector. Okay, so first of all, let's see. So now we're gonna. So how do we take the partial derivatives to this? That's a good question. We can't do it similar to the old thing. So what our natural instinct to do is split up these into two scalar functions. So we'll have some f1 equals 2x minus y3, that's the first row, and then have an f2, which is ex minus 13y, so that's the second row. Alright, so now we can take the derivatives of x with respect to x and y of both of these functions. So you'll see what I mean. So let's take the partial derivative of f1 with respect to x first, so that's going to be here. So that's going to be 2 equals 2. And then let's take the partial derivative of f1 again, but this time to y. So this one is going to be negative 3y squared using the power rule. And then, so we got all the partial derivatives for our first function. So now we want to worry about our second function. So f2. So our partial derivatives of f2, we're going to do the exact same thing with respect to x. So now it's going to be ex, so we're going to have ex. And then we're going to have f of 2, but this time to y, and we're going to have that equal to, what is our thing? So negative 13. So those are going to be our partial derivatives, all four of our partial derivatives. So we need 2 for each function. So basically, the Jacobian is how we display these partial derivatives, not dissimilar to how the gradient worked. So remember how the gradient was vertical, a vector, where you had the derivative with respect to x and then derivative with respect to y. Well, now that we have 4, we're going to have a matrix, and that's going to be called the Jacobian. So let's just look at it here. So before I draw it, let's just kind of see what we're going to be expecting. So it's going to be similar to this in terms of orientation. So we're going to have all the derivatives with respect to f1 here, and then we're going to have all the derivatives with respect to f2. And obviously, if you have more rows to this vector, you're going to have more output equations, and this is going to go on for however long. But yeah, the rows are going to be the functions, and then the columns are going to be the variables. So you can think of it almost as the gradient of f1 and then the gradient of f2 as the rows. You can see why, but obviously, I guess to be exact, you want to be it's the transpose of the gradient, is you're taking a column vector and turning it into a row vector. Anyway, so let's just kind of fill in what this would be for us. So just to kind of make it concrete, let me draw out those partial derivatives as variables. So it'd be f1 and then x, and then f1 with respect to y, and then it's going to be f2 here with respect to x again, so it's same column, same variable, and f2 with respect to y. That looks right. So it's going to be the functions and then the variables. So if you had more variables, it would be longer this way. If you had more functions, it'd be longer this way. So in our case specifically, we would have 2, then we'd have negative 3y squared, and then we'd have, you can see all those, e to the power of x, and then we would have negative 13. Nice. So that's going to be our Jacobian. I think that's all you need to say for the Jacobian. So that's going to be however big you want. A good thing to note is a lot of the time, and I'll explain this later, but these will end up being diagonal vectors with just zeros along the edges, which makes computation a lot quicker, but I'll explain why that happens and when that happens. Anyways. So next on, let's move on to the Jacobian chain rule. So you've already seen the scalar chain rule, I hope, and are familiar with how to differentiate a function using the scalar chain rule. But I just want to kind of introduce a kind of a new way of looking at the scalar chain rule that'll help us differentiate larger functions and get comfortable with Jacobians and that sort of thing. So the Jacobian chain rule and that sort of thing. So scalar chain rule. So if we have some function that we can do the chain rule on, so sine of x squared, normally what we would do the derivative of the inner function times the derivative of the outer function, so we get 2x cosine of x squared. But there's kind of almost a slower way with smaller functions, but kind of methodical, algorithmic way that we can kind of apply to any function. And that's splitting this up into two functions. So what we can do is we can split this up into two functions. So we have, this inner function x squared, let's set that equal to g. And then let's set this outer function to f sine of g. So if we plug that in, it's the exact same thing here. So what we do is we find the derivative of g. So to find, what we're trying to find is the derivative of f with respect to x, right? We're trying to find how this changes when you change x. So usually we did this in a kind of very quick way, but let's kind of do this methodically. So what we do is we find how f changes when we change g, and then we see how g changes when we see x. So this is really what we're doing with the chain rule. We're kind of breaking this up into two functions and finding the derivatives of both of them. So this is just an interesting way to look at it, so let's just kind of carry through. So the partial derivative with how g changes with respect to x is going to be, it's going to be 2x. So it's going to be 2x. So it's going to be 2x, and then how f changes with respect to g is going to be cosine of g. So the change in f with respect to change in x is going to be equal to cosine g times 2x. But then our last step is to substitute, so we substitute any intermediate functions that we created with whatever it was equal to, so it would be cosine of g, so cosine of x squared, and then 2x. So that's the exact same answer. I think I erased my original answer, but it's the exact same answer that we get by doing this kind of intermediate function kind of way of seeing things. So when we have a very nested function where we have some g of f of x of c of a of x, I don't know, I had an x here, h, why not? We have some super nested function here. What we can do is we can set all of these inner functions to intermediate kind of function variables, and then find the derivatives of all of those, and then multiply, and then substitute at the end. So that's just kind of a new way of seeing, or you might be familiar, but kind of a more algorithmic view of the scalar chain rule that'll work for more for a lot of different functions. So just like assign all the inner functions with some variable, and then find all the things, and then do that. So this will help us look at the Jacobian chain rule, which we'll look at next. Alright, so how can this idea help us deal with vector-to-vector functions? Well, looking at this example here, sine of x squared plus y and ln of y cubed, we can see that both of these are functions that would generally require the chain rule if you were dealing with them by themselves. Of course, here you would compute the outside, so it would be the derivative of the outside, so it would be cosine of, the drill, cosine of x squared plus y, multiplied the derivative of the inside. So derivative outside by derivative inside. So we can do something similar here that we did with our example before. So we can set an intermediate variable for these insides and turn this actually into a vector of intermediate functions. So we can say x squared plus y and y cubed. So those are the two intermediate functions from these two. Alright, so now we can set an outer function vector. So we can say sine of g1 and ln of g2. Perfect. So obviously that makes sense because this is g1, similar to what we were saying f1 and f2 before. This is g1, this is g2, so if we substitute these into here, we get back this exact same vector. Okay. Well, great. So what do we do from here? So what we can actually do is compute the Jacobians of both of these. Just make a little space for that here. Alright, so let's compute the Jacobian of g. And I kind of get used to this notation. So the Jacobian of this is going to be how g changes when we change x and y. So to be specific, that's how g1 and g2 change when we change x and y. So how we can represent this is the change in g, which is a vector now of g1 and g2, when we change x, which now is a vector of x and y. So that's kind of some new notation that's important. So obviously we can take this first function here, g1, and see how that changes with x, so that's going to be 2x. See how it changes with y, which is going to be 1. See how this changes with x, it's going to be 0, because there's no x in this row. And how it changes with y, which is going to be 3y squared. Awesome. Okay, so now let's do the exact same thing for the second function, the second vector. So now we're going to be finding the change in f when we change g. Okay, so now we're going to be doing another Jacobian so instead of our variables before being x and y, now our variables will be g1 and g2, because those are our inputs to this vector. Okay, so let's take sine of g1 with respect to g1, it's going to be cosine of g1. Sine of g1 with respect to g2 is going to be 0. ln of g1 is going to be 0. Ln of g2 with respect to g1 is going to be 0. And ln of g2 with respect to g2 is going to be 1 over g2. Great, so now that we have these two Jacobians, what can we do with them? Well, you might remember with the scalar chain rule, I'm just going to keep that up here. With the scalar chain rule, remember scalar chain rule. Remember the scalar chain rule, we could find the derivative of some, let's say y, with respect to some x, if we have the derivative of that y to some intermediate u, and that intermediate u with some x. You can almost think of them crossing out, and we can have a y with respect to an x. So, keeping that in mind, we can actually do the exact same thing with the vector chain rule, with Jacobians. Well, now that we're familiar with this notation, we can see how that comes about pretty easily. So right now we're trying to find the change in the f vector, which is this, when we change the x vector. That's going to be the Jacobian of this. So that's going to be the Jacobian of this multiplied by this. And with matrix multiplication, it's really important to get the order correct, because if you multiply some matrix A times some matrix B, that's not equal to a matrix B times a matrix A. So we need to be really careful about our ordering. So what we do with the Jacobians when we're multiplying Jacobians for the Jacobian chain rule, we want to start with the outer functions first. So we're going to find the change in forgot my partial sign. The change in f when we change our g, and then how our g changes when we change our x. Oopsies. So obviously this Jacobian here is this, and this Jacobian here is this. So we can just directly substitute those Jacobians in and see what we get. I try to keep this small because I always run out of space. Alright, so 2x, 1, 0, and 3y squared. See, I can run a room again, but I'll kind of erase these because we got these now. And then we're going to multiply this by, sorry, I actually did exactly what I'm not supposed to do. I was switch around the orders of these. So that's an example of what you shouldn't be doing with the order. You should be starting with the outside one, so that'd be cosine of g1, and then 0, and then 0, and then 1 over g2. And then we're going to be putting the intermediate function at the end, so we're going to be putting 2x, 1, 0, and 3y squared. Alright, so now we just can do a simple matrix multiplication of these two to get our answer. So what we're going to do is we're going to keep this here, so we're still trying to find the change in f when we change x, and we're just going to do a simple matrix multiplication here. So we're going to do this row times this, so we're going to get 2x cosine of g1, and we're going to do this times this, so that's going to be cosine of g1. And then we're going to do this times this, so that's going to be 0. And we're going to do this times this, which is going to be 3y squared over g2. And I like to just kind of do a mental check of this. Does this make sense when looking at this? Always, I'm kind of suspicious of zeros, but zeros are a bit weird, so we want to make sure that this 0 makes sense. So why is there a 0 here? So what does this mean? So this column is the change in x. So why doesn't the change in x affect the second function? Well, just looking at it, there's no x here. So of course there's not going to be a change in this when we change x, but it's completely not related to x. So we can kind of assume that I did these all right. I'm pretty sure I did. Hopefully. It'd be awkward if I didn't. And the last step here is going to be substituting these g1s with the actual intermediate functions. So let's go ahead and do that. So it's kind of confusing, but this is going to be our final answer here. Alright, so our change in f, when we change x, is going to be exactly equal to 2x cosine of x squared plus y, cosine of x squared plus y, which is our g1. Kind of running out of room there, hopefully you get that, and 0. And 3y squared over our g2, which is y3. we can actually simplify that into y and 3 over y. Okay, so great. So this Jacobian here is the change in our f when we change our input vector x. So this is our final answer that we got through using the chain rule with Jacobians. And there's just one thing I want to mention that I was kind of confused about when I first learned this, and I kind of had to figure it out myself because there wasn't many resources on it, was what happens when not all of these vectors, let me just make this really clear because we're done with this now. So one thing I was kind of confused on is what if not all of these functions, what if they weren't all kind of chain rulable or whatever? Like, what if you could not use a chain rule on all of them? So let's say we had another one, x, y, 3. So you wouldn't be using the chain rule on something like this. So what would that intermediate function, that intermediate vector look like? Well, all it would look like is you would have g sine, so then you'd have your normal x squared plus y, and then you have your y cubed just like before. But now instead of, there's no intermediate function for this function here, so I would just put 1. So that's just something to keep in mind when you're multiplying out these Jacobians. When you have a function that doesn't have an intermediate function and you're computing, because that's going to happen a lot. You're not always going to have chain functions that use the chain rule. You just leave a 1 here and that makes all the multiplication afterwards safe. So that's all I want to mention there. That's really all you need to know about the Jacobian chain rule, and all. Basically, that's basically the extent of calculus you need to know for this. But I'll explain the derivatives of some special operations and the Jacobians of some special operations, like the Hadamard, what was it called, the product of product of two vectors and stuff like that. In the coming parts, but that's all you need to know for preliminary knowledge. Alright, so I'll see you in the next part. Alright, so let's just jump straight in with neural networks and neurons. This is exciting. This is our first actual neural network stuff, so let's get started. So first of all, I'm going to describe how we can mathematically kind of explore the concept of a single neuron in a neural network. So let's just jump in with an example. x1, x2, x3, x4, x5. So these are going to be the inputs to a single neuron n. Awesome. So all of these inputs are connected to this neuron by some weight. So W1, W2, W3, W4, you get the program, W5. Alright, so what our neuron will do, it will take the weighted sum of all these inputs. So it's going to multiply an input by its corresponding weight. So it would be x1 times w1 plus x2 times w2 plus x3 times w3. You get the program. So let's multiply this. So to describe this, it'll be the summation of bi equals 1, and then up until n. Remember, n is the amount of input variables we have. And then we'll do xi times wi, and then we'll add our bias. So that's going to be describing this mathematically. So that's basically what I said. So we sum over all of our inputs. That's basically what this means. We go from 1 till n, and then we multiply the first input times the first weight, and then we multiply, and then we add that to the second weight times the second input, and then we add that to the third input times the third weight, and then you get the point. So we end up with a single scalar here. That's kind of the most important idea. We end up with a single scalar, so this evaluates to a scalar. And then we have this bias here. So this bias is just a term that is attached to this node. It's a scalar that we add to this node, so I don't know what this is, but let's just keep that as b. So that's also going to be a scalar. So we can see that these scalars will add together, obviously, to be just one scalar. And this sigmoid function, well, I use the sigmoid sign, but now the sigmoid function isn't super popular, as they're called activation functions. So I'll just call this an activation function. I'll use the sigmoid sign, but this can, there's multiple different, there's the sigmoid function, which is a little more old and not as popular now. Now most people use the it's such a cumbersome name, but the rectified linear unit, or ReLU, which looks like this, which basically makes all negative values of this 0, so it goes like this. There's lots of different functions that you can use. Let's just say we're using the activation function. I'll talk about that later. So just some more notation. Anyway, so yeah, so we got that down, right? So we can actually, we can do something more. So we can describe this in a slightly more understandable way using dot products. So this summation is kind of, it's kind of a pain to look at. So instead we can talk about the dot product of two vectors. So obviously the dot product of two vectors, just to review, let's say we have some vector 3, 2, 1, and then we have some vector 4, 5, 6. The dot product basically means transposing one of these and multiplying it. So we end up with the important part of a dot product is we multiply two vectors and end up with a scalar. Sometimes it's called the inner product. So let's say we transpose this one. It doesn't really matter which order. And then, sorry, I was running a room in this tiny whiteboard. 4, 5, 6. Alright, so and then we multiply that by 4, 5, 6. So then we multiply this times this, plus this times this, plus this times this. So that would be 3 times 4, 12, plus 10, so that would be 22, plus 6, so the scalar output of this dot product would be 28. Alright, so that's just a super quick review on what a dot product is. So that might kind of seem relevant to this discussion about sums. So we can actually describe this as a dot product instead. If we have two vectors, let's say we only have two, I'm not going to count, so xn. And then we have another one, which is the weights. So weight 1, weight 2, weight n. So for now, n will be 5, right? So then we can take the inner product of these, which is going to be the exact same thing. So we're going to be multiplying the first input by the first weight, and then adding that to the second input times the second weight. So that's going to end up looking like x1, w1 plus x2, x2, w2 plus x3, w3, dot, 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 all the way to xn, wn. So that's exactly, when you think about it, exactly what this summation is doing. So we can replace this with some simple notation for dot product, which, as I said, we transpose one of these and then we multiply it by the weights. So it really doesn't matter which order you do. I'm going to do x transpose w. So we're going to transpose x and then multiply it by w, so that's going to be a scalar still. And then we're going to end up with this bias plus b. Alright, so simple enough. So that's kind of the simplified notation for a single neuron using dot products. Alright, so that's nice. So I just want to kind of hit on one more key central idea with this. So this, and one kind of thing that's going to come up often is this inner part here is going to be z. So we're going to call this inner part z. So we can actually kind of represent this neuron in two steps. We can represent it in x transpose w times b, so that's kind of the weighted sum part. And then we can make this equal to z. And then our second part can be putting it into our sigmoid or our activation function. So then the activation of this neuron, which is going to be a, and we're going to add some more superscripts and subscripts once we get more and more neurons, but let's just keep it simple now. So we're going to, it's just going to be the activation function with z. So we can represent this in two steps. It's often represented in two steps for reasons we'll see later. So just the key idea I want to get across here is that this single neuron is basically a function that takes in a vector and outputs a scalar. So it's a vector to scalar function. And that might think, oh, gradients, and it'll kind of get your mind going. But it basically inputs a vector, and then you get a scalar. That's all it is. That's all a single node is. So that's just kind of what I want to get across. Next up, we'll look at layers of neurons and how that can be represented with entire matrices. So that's very important, so stick around. Transition. Alright, so one thing I just want to get out of the way is the notation for the weights of a neural network, which can be a bit tricky at first. So let's say we have an input x1, x2, and then we have these two neurons. Let's say maybe another layer of neurons. And then we end up with an output. Alright, so generally, so now that we have, before I just said W1, W2, W3, whatever, but now that we have multiple nodes, you can't say W1 because is this going to be W2 and then what are the other ones going to the other node going to be? It's going to be a headache. So basically what we're doing is that we're going to split this up into something in this notation, WL, JK. Okay, so what does this mean? So this is going to be the standard notation for any single weight in our network. So here, L equals the layer weight is going into. And I already said this before, but it's just worth reiterating here. So J is the number of the neuron in the layer that it's going into. Okay, so let's just say node in layer L, and the K is going to be the node in layer L minus 1. And there's kind of a reason for this notation, but it might seem a little weird, but let's just take an example to make this a little more concrete. So let's say that we have we want to establish what this weight here is. This weight. What is that weight? How can we represent this notation? So let's say this is layer 1, this is layer 2, and this is layer 3. So let's try to represent this weight. So what is it going to be? So it's going into layer 2. So we can say the 2 is up there. And so the node in layer L, which is going to be 2, so it's going into the second, it is going into the second node in layer 2. So we can make J equal to 2. Again, we have a node, and then in K, we have the node in the layer before. So which node from layer L minus 1, which is 1, which node in this layer is it coming from? Again, it's 2. So that might be a bit confusing example because we have a lot of the same numbers, but it's a weight that goes into layer 2 that comes from the second node in this layer and goes into the second node of this layer. Let's do just one more example. Let's take this one. This node. This weight. Alright, so again, W. So now it's going to layer 3. So W3. So the K is the node in the layer before, so where is it coming from? It's kind of confusing because the K comes after the J, but the K is the node it comes from in layer 2. So it comes from the first node in the layer before. So it comes from the first node in layer 2, so it's going to be K equals 1. And then J is the node that it goes into, so again it's going to be 1. It's going into the first node in this layer. Alright, so just some super lightning fast examples. This one would be W, and you can kind of think about it for a second. It would be W3, and then node in layer L minus 1, it'd be 2. So it'd be 2, and then it's going into 1. Alright, that's the last example I'll do. There's a lot of different resources that explore this sort of thing, so you haven't gotten that. It's really important to get that down. So I guess for practice, I'll put up a couple here, and you can think about which weights these correspond to. Alright, so I'll let you do those. Alright. Okay, so now we want to dive into, it's a lot easier, don't worry, but the biases of this. So generally biases are the same for each node in a layer. So maybe this bias will be 5 for this layer, and maybe it'll be 6 for this layer, maybe it'll be minus 73. I doubt it, but who knows. It'll be a scalar for each layer. So generally the bias for one layer is signified by BL. So for if here it was 5, so B1 would equal 5, generally. Sometimes you see it that we have BL and then sometimes it's N, It's a lot of different numbers. It can, let's just say j. Sometimes this shows up, which means that in this scenario, different nodes might have specific biases. This is used sometimes yes, sometimes no. So take what you will. So I guess if this bias had specifically a 5 attached to it, and maybe this one had a 3 attached to it, then B1, 2 would equal 5, and B1, 1 will equal 3. Alright, so that's just some simple stuff. Mostly I'll be using just this, but that's good to keep in mind. What else is there to think about? I think that's about it for notation. If there's anything that pops up later, I'll be sure to mention it, but that's all you need to know for notation. So weight notation, bias notation, can be a bit tricky, but you'll get used to it. Alright, so let's just dive in with some matrices and how this actually operates. Alright, see you on the other side. Okay, so now that we have the notation down, we can actually jump into seeing how we can represent the computations for an entire layer of a neural network. So remember how before we had the one neuron and then we had the, we had the 5 inputs to that one neuron, and we explained how that the output of this neuron is a vector to a scalar function. Well, when we're thinking of large networks of neurons, so say we have maybe 3 neurons here, and then we have x1, x2, x3, x4, x5, b4. So now each of these inputs go to a node, and they have their own corresponding weights, so let's just draw that out. So each of these inputs is connected to one of these nodes by a weight. So each of these nodes is receiving a weighted sum of these inputs and their weights. So I guess you can see maybe this node here, it has 5 inputs, which are these 5 multiplied by 5 weights that are specific to this neuron. So since we saw that a single node takes in a vector of inputs and then multiplies it by a vector of weights and then puts out a single scalar, and then this one is going to be multiplying its weights by the same inputs and going to be giving another scalar, let's say that's S3, and this is going to give another scalar S2, and this is going to give another scalar S1. So these scalars form the new vector of inputs, just like the x1s, into our next layer of our neural network. So we send each of these to some neuron, and then we're going to have the same thing. So these scalars that are outputted from these are actually going to become a vector, and this vector we like to call AL, which is the activations of layer L. So if this is layer 1, this would be A1. So you might think that, okay, now that we have this notation for, not really notation, but this intuition as to what is happening with multiple nodes, how can we represent this? Because remember that we represent a single node with this. We explain it as the transpose, right? So it would be X transpose W plus B. Right, that was a single one where this is a vector, and this is a scalar, the bias, right? And then you put that through some sort of activation. Well, now we can represent the weights of an entire layer with a weights matrix. So this looks like a capital W. We usually use capital letters to signify matrices. WL. So this takes care of, for example, all the weights in this entire thing for going from each input to each node. So how do we do that? Well, let's make some space. So this weights matrix W. So one thing to think about this weights matrix is that looking at our old notation for a single weight, how to locate one weight in an entire network is using this notation that we just learned. So remembering that J is the number of the neuron in the layer that it's going to, and K is the number of the neuron in the layer that it came from. So I won't review that again because I just reviewed that, but you can go back and check that if you haven't got it down yet. But when we're looking at this weights matrix, each entry in this weights matrix goes a bit like this. I put it here just to remember for you and me. But looking at the rows of this weight matrix, so the rows are the J, and the columns are the K. So something in here, so in the Jth row in the kth column, comes from the comes from the kth neuron and goes to the jth neuron. That might be a little hard. And the whole thing is layer L. So this entire matrix is layer L, and this describes coming from node K. So here, if K was equal to 1 and J was equal to 1, this was the position of this one, it would be coming from the first neuron in layer L minus 1 and going to the first neuron in layer L. So if we were to write that out, so this 1, 1, if we were in an easy neural network like this, and we were going from this to this 1, 1 would be going from here to here. It would be going from the kth neuron, the first neuron in layer L minus 1, to the first neuron in J, which would be L. I mean, the jth neuron in L. Does that make sense? It might be a little easier with an example, so let's just take an example. I'm going to just make a super little simple neural network, and we're actually going to compute the weights matrix by hand just to see how that goes, just to kind of better understand what's going on here. So let's take a simple little neural network here, and we're going to actually put some real values for the weights just to get a better idea of what's going on. Alright, so we got a super simple neural network here. We got our inputs going in. Let's get rid of that. We've got our inputs going in here. Alright, so the inputs go into these ones and just one layer, and then they process something and then goes into here. So how do we describe these weights here? This first layer of weights, W1. Well, okay, let's give these nodes value, give these weights values. So let's say this weight going from here to here is 5. Let's say this weight from going to here is 6. Why not? And let's say this weight going from x2 to node 1 in the first layer is going to be 2. And then this one going from here to here is going to be 3. So hopefully you got that down. So this to here is 3, this to here is 2, this to here is 5, and this to here is 6. Okay, so now that we have that, let's see if we can construct a weight matrix for this layer. So let's create a weight matrix 1 because it's layer 1. It's the first set of weights. So this is going to be 2 by 2. So remember that the columns are the K. So the columns are which node in this layer, sorry, the K is where it's coming from. So it's which input is it coming from. So if it's coming from the first input to something, it would be in the first column. If it was coming from the second input, it'd be in the second column. So now we can look at J, which is the rows. So if it's going into the first node, it would be going in the first row. If it was going to the second node, it would be going to the second row. So that's kind of how we locate something here. We can locate it by its position. So what's here? So this is the 1, 1 position. 1, 1 position. So this would be going from k equals 1 to j equals 1. So going from 1, we're going from k equals 1 to j equals 1. Which weight does that? It's 5. So here's going to be 5. Next up, we're going to go from the first row, so 1. We always index matrices row and then column. But that's, you should probably know that by now. But this is the row, right? So we would be dealing with what's here. So this is 1, 2. So this would be going to node 1, but it'd be in k equals 2. K equals 2. So that would be coming from the second input going to the first neuron. So that would be what goes from here to here would be 2. Just the reason why that is because it's in the second column, which means that it's coming from the second input, because that's the columns are k, and then the rows are j, so it's still in the first row, which means it's still going to the first node. Okay, so now let's deal with this one. So this one's 2, 1. The percentage of this is 2, 1. Pressure of this now is 1, 2 as well. So this is going, so the k is equal to 1, so it's coming from the first node, but now the row is equal to 2, so it would be going to the second node, so that'd be 3. And then now we're going from the second node to the second node in the other layer, so that would be 6. Okay, so hopefully you got that down. So this is the weights matrix, and I'm just going to draw out the notation for, so remember how we had that W transpose X plus B notation for the function of a single neuron? we can now represent the input to an entire layer and the output of an entire layer as the following. So that's our weights matrix. So L times A, L minus 1 plus B, L. So I'll explain that a little bit, well, in a couple minutes. Well, I'll kind of play this out, but let's actually do this and see why this works. So, this A, L minus 1, by the way, is the activations of the previous layer. So remember how we were talking about when you have a whole layer of neurons, those scalar outputs become a vector? So that vector would be an A vector. So for the first layer, our A is the X inputs. But for the second layer, the A will be the outputs of the first layer, and so on, so on. So a lot of the time, we represent the X input as either A0 or something like that, because it's just kind of the first activation. You can almost think of it like that. So we have this calculation. So why does this work? So let's say our inputs are like 2, and let's take some unique numbers maybe. Let's take 10 and 20. So those are our inputs, 10 and 20. So, these numbers might get a little big, but let's see what happens. So, this formula tells us to multiply this weights matrix by the activations of the previous layer. So, multiplying these weights by these inputs. So, let's try that. So, that'll be 10 and 20. So, x1, x1, x2. So, 10, 20, the activations of the previous layer. So, to do a matrix multiplication, so this is obviously a 2-2 matrix and a 2-1 matrix, so our output's gonna be size 2-1. So our output's gonna be a vector, and that matches up to what we're thinking, because the outputs of this layer should be a vector of 2 numbers representing the activation of this and the activation of this. So these are 2 scalars outputs, and those become a vector, which will be represented in a 2-by-1 vector. So that should make sense. So it's making sense so far. So what else do we do in this formula? So now we multiply it by that. So let's do the matrix multiplication. We'll get a 2-by-1 vector. So 5 times 2 is going to be, but let's just think about what we're doing here. Right, so we're multiplying this weight by, well, we're multiplying this weight by this input and this input. So what does that mean when we're looking at the actual weight? So 5 is the one connecting here to here. And 2 is the one connecting from, 2 is the one connecting from here to here. Is that correct? Yes, that is correct. It's going from the second node to the first node. So as you can notice that multiplying this times this calculates the weighted sum going into this neuron. Because this neuron takes in this input and this weight, and this input and this weight, and multiplies and sums them. So when we're multiplying this times this and summing them, we're doing the exact same thing that we were dealing with when we were doing a single neuron where we took the dot product. So multiplying this and this is kind of like taking the dot product of the inputs, x1 and x2, with the weights going to node 1. So it's the exact same thing. So we get the scalar output of this, which is going to be 5, so it would be 5 times 10, so 50, plus 2 times 20, so that would be 40 plus 50, which is going to be 90. That's a big output. So the activation, well, so far, because we haven't added the bias yet, so it's just this part. So far, for this node is 90. So far the W transpose, do you remember in the single neuron we have the W transpose X? So currently the W transpose X of this is going to be 90, because it's the weighted sum of our inputs and the weights into this neuron. Because 5 and 2 go into that, and we multiply 5 and 2. So now let's do the exact same thing for this one. So it's taking the weighted sum of all the weights going into this node. So that's going to be 3 and 6, and that works out 3 and 6 very nicely here. So we're going to multiply 3 times 10, it's going to be, I've got to regret choosing such big numbers, 30, and then 120, so that's going to be 150. Okay, so we're going to multiply that by that, and that's the exact same calculation. We're taking these inputs and we're multiplying by the weights going into this neuron, which gives us the exact same thing of doing the dot product with a single neuron. So by using this matrix multiplication, we can kind of do the exact same operation but all at the same time, so that's a lot easier. Next up, we add our bias, and this isn't that important because, it's pretty easy to understand, it's not that new, but let's just kind of, keep going with the example. So usually, a bias is the same for the entire layer of neurons. So let's say the bias for the entire layer is plus 6. It can be a negative number, but let's say it's plus 6. So we add 6 to each of these results, so we get 96 and 156. So now we've calculated this entire inside, which we often call z. So we can say that z1 equals this vector of 96 and 156. But we have one more step. We have the activation function. I'm just going to go through all of this with you so you can kind of better understand what's going on. Obviously, I'm not going to be doing this with larger neural networks, but this kind of gives you a good idea of what's happening. So we have this output vector z1. So now we just have to put this z1 into an activation function. So this is basically what we're doing now. We're just putting this z1 into an activation function, and then this is actually the vector 96, 156. And so this activation function can be any kind of nonlinear function you want. I guess a popular one now, and it's kind of easy to compute for me, so I'll use it, is ReLU. So we'd have this thing. So basically, z is equal to z, unless it's negative. If it's negative, z is equal to 0, pretty much. So both of these are non-negative, so when we're putting them through the activation function, it actually stays the same, because z equals z, if it's, it just goes up. As opposed with the sigmoid, where it's either 0 or 1. So if we were using the sigmoid, these would be close to 1, I would say. But let's use the ReLU. That actually works better. It's been proven to work slightly better. But anyway, so we have this, right? So 96, 156, after going through the activation function, is still 96, 156, and that's our scalar output for this layer. So now we can say that A1 equals this. So then again, we can think about putting that in the next layer. And so A1, so remember before we had the x as our thing in our function. Let's just kind of keep that up here, just because it's important. So remember how we used to have our x's be this. So in the next layer, we would have our new weights matrix, and we have this. And you kind of see how this works, and this would work in a much bigger scenario as well. And you just keep going through the network and doing that. So just one more thing on how I represent neural networks. I find that it's a pretty easy way to kind of represent multiple layers of a neural network. Of course, the visual way is to write something out like this, some sort of graph, but kind of a quick and easy way, and actually really helpful when you're trying to derive things, is kind of writing a chain of these multiplications. So kind of an example of something like that would be, okay, so we have our inputs, right? So let's call these inputs A0. So, and then it's just kind of a string of calculations, kind of expressing multiple layers of a network as just lots of different calculations of this same thing. So we can say, oh, we put this into this, and we have W1, and then A0, and then plus B1. Right, so this calculation, although it may seem small, calculates the entire first layer, the output of our entire first layer of our network. So remember that we're still dealing with single training examples here, so our input A0 is a vector. So this vector gets fed into this, and the output is another vector. Because if we have multiple neurons, each of those is going to set out a scalar, and that will become a vector. So this tosses in a vector and takes out a vector. So it's a vector-to-vector function. And remembering what Jacobians are, you can start to think about what the implications of that are. But we put a vector in, and we take a vector out. So this vector A1, so the output of this would be A1. So now we can put this into another layer of the network. I'm just going to erase this so we have some space. We can now toss this to another layer of the network and get W2, so our new weights matrix times A1 plus B2. Sorry, I'm using subscripts now, sorry. There we go, so that's our second layer of the neural network, and we can just keep going. And I'm going to be using this kind of notation quite a bit, just because it's a lot easier than drawing out all this. So yeah, so I think that's enough to say about how we can compute neural networks. So this is kind of, I guess, the feed-forward aspect. I never really mentioned that word, but this is feeding forward a neural network, feeding an input through the network the first time. So we have a network like this. Now we're going forward, so we're feeding the input forward through our network. So we're just getting an output. So at the beginning, before training our network, this output is going to be really crappy. But as we'll see later through backpropagation, which will be going backwards, we'll be improving the weights and seeing how we can make this feed-forward output better. So at the end of the day, once we've fully trained our network, that's all we're doing. We're just feeding forward. So if you have a fully trained network, we can feed forward, say, an image, which is just a bunch of x1s, x blah, 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 xn, and that comes out to be some sort of classification or an answer. So right now we're focusing on the feed forward, but we're going to quickly dive into the backpropagation since the feed forward aspect of neural networks is not too hard to grasp. But we kind of covered it pretty quickly here. But if you want more details on that, definitely there's resources for that. And I'll probably put them in a link in the description. So I'll see you next time. I'm not really sure what we're going to do next, but you'll see in post. So yeah, see you soon. Alright, so now that we've covered the feed forward aspect of a neural network, or how we can feed our input forward through our network, now we're going to focus on backpropagation, and that's kind of the focus of most of this lecture is backpropagation, just because it's a little technically harder to grasp and mathematically harder to grasp as well. So we're going to be seeing how we can lower the cost of our final output, or the accuracy, or the error, minimize the error of our output by changing the weights and the biases in our entire algorithm. So how we're going to do this is by going back through the network and seeing how each of these weights in our network affect the total costs. So if we tweak this random weight in our network, will that increase or lower the final cost? And using that information, we can tweak those weights and biases accordingly and get a better answer. So that's basically the entire goal of backpropagation. So the first thing I kind of want to cover is just the cost function, and this is just a quick introduction, and I'll go much more in depth in both of these over the next however long this ends up being. But one thing I just want to cover now is the cost function we're going to be using, because I'm not going to go into that too much. The name of this cost function is one of the most popular, or the most popular cost function, is called mean squared error, so you might be very familiar with it. Basically, we cycle through every single one of our outputs, and then we compare them to our actual real answers, and then we square the error, and then we sum over it. So basically in numerical terms, we take a summation of m, all of our training examples, if we put multiple examples through the network and we want a total output cost, and then we have I equals 1, and then we have our x output, so it's going to be, well, what's a good letter for that? Most commonly used is y hat, so y hat will be the total output of our network, so we're going to take y hat and negate it from the actual answer and square that. So that's what mean squared error is. So we take our answer that we get from feeding forward, and then we're going to take the actual y answer associated with that training example, find the difference, and square that difference. And then, I forgot a part, this is the most important part, it's where the mean comes in. We're going to be taking the mean, or just 2 times the mean, 1 over 2 times the mean, in our cost function. And the reason why this 2 is here, which puzzled me when I first figured it out, the reason is when you try to derive the cost function, and if you're familiar with deriving it, you'll notice that the 2 comes out because of the power rule, so this 2 cancels out with this 2. And that just makes calculations a little nicer. So that's the reason why it's 2 here. And that doesn't affect calculation whatsoever, because you're multiplying everything by 2, so it really doesn't change anything. Anyway, so this is the cost function we're going to be using, the mean squared error cost function. Other than that, we're going to be dealing with a very simple scenario at first. I'm going to call it, I guess, the simple model. And it's going to be really similar to the one we just saw. It's going to be x1, x2, x3, x4, and x5, so 5 inputs going to a single neuron. So this is going to be a vector turned into a scalar output, so the activation of the single neuron, and we're just going to put this into a cost function. So we're just doing a very, very simple neural network with a single node. And this is how we're going to first kind of explore how changing these 5 weights, plus the bias here, is going to change our cost. And we're just going to kind of explore this idea of using Jacobians, of what we just reviewed at the beginning, and seeing how we can calculate basically the derivatives of the cost function with respect to each of our weights and our bias, and seeing the derivatives of each of these, and just seeing if we change this, how will this change? If we change this, how will this change? And we can use that to better tweak these weights and increase the accuracy or lower the error of our final output. So we're going to do that by calculating the derivatives, and we're going to be talking about gradient descent. So how can we use these derivatives to create an algorithm to automatically find the lowest cost? So hopefully this sounds good, and next up we'll dive into how do we start to, using the laws about Jacobians, how do we start to derive the operations that go on in a single neuron. So look out for that. Alright, so now that we've talked about the operations that go on within a single neuron and a layer of neurons, now we're going to try to find the derivatives of these different operations so we can go back and try to find the derivatives of an entire neuron with respect to the weights and the biases. So how do we start doing this? Well, let's start with, so there's three different things I want to talk about here. I'll leave this one for after the first two, because these first two are kind of tied together. We're going to try to find the Jacobians and derivatives, well, they're the same things, of binary element-wise operations and the Hadamard product. The Hadamard product actually is a binary element-wise operation, but I guess a good question to ask now would be, what is a binary element-wise operation? So, a binary element-wise operation is some sort of function that takes in two vectors v and w, and returns a single vector, let's call that, what's a good, b? Why not? Alright, so what does this mean? So there's a few more restrictions on what it needs to be. It needs to be, it's pretty self-explanatory. The operation that you do on these v and w needs to be element-wise. So if we have some vector v, and we have some vector w, and we're doing some element-wise operation between them, it needs to be element-wise. So it has to be an addition, so the output of this function needs to be maybe this first element of this plus the first element of this equals the first element of this, second element of this, second element of this equals the... So this could be an element-wise multiplication, this can be an element-wise comparison, so the output could be like a 0, 1, 0, 0, 1, where when the output is 1, that means that's this element of w is bigger than this one, so this is true. So basically a true-false, like Boolean output, or it can be just a normal sum. Notice that our Hadamard product is a binary element-wise operation when we're using a multiplication. That's exactly the definition of a Hadamard product. So yeah, those kinds of things. So how can we take the derivative of a binary element-wise operation? And obviously binary is binary because there's two vectors involved. Well, let's put this in our standard function notation. So let's take some VW, and then say in explicit notation f of v, and then some sort of operation, some sort of element-wise operation, and then g of w. So the reason why we have these f and g's here is that sometimes we might want to do something on the vector before comparing it. So for example, maybe you want to multiply every element in v by 5 before comparing it to g, comparing it to w. Or we maybe want to multiply every element in v by 5 and every element in g by 6, or maybe you want to take the log of every element. But the thing is, these functions don't have to be element-wise. This total function, let's actually change this to a capital F. This total function needs to be element-wise. This operator needs to be element-wise, but these operations here don't. So, for example, maybe this function could do something where if you had some vector v, each element in v became like the sum of all the previous elements, or something like that. It doesn't have to be, this mini function in a function doesn't have to be element-wise. And you might ask, why are we including these mini functions in this big function anyways? It's just for the sake of generality. Sometimes we might want to alter our inputs before doing some element-wise operation. Often not, like the Hadamard product, we just directly multiply v and w element-wise. So in this case, f and g would be constant functions, where f of v equals v, and g of w equals w. And you'll see a lot of the time in element-wise functions, this is almost the most popular and common case, is where these f and g functions just do nothing. but, you know, it's good to be general and, you know, make sure that we cover all different cases. So how do we take the Jacobian of this? Well, when looking at this, usually at the multivariable functions that we were looking at in the introduction, we were passing just single vectors into the function, so maybe some x, y, which is like a 2 by 1 vector, but now we have two vectors. So what does that mean? So that means we can get two Jacobians out of this, one with respect to the elements of v, and one with respect to the elements of w. So we're going to end up with two Jacobians, so this will be one of them. This will be all the elements of w, and this one will be all the with respect to all the elements of v. Awesome. So we'll just find one of these. I think I'll do v. It really doesn't matter, but at the end I'll tell you how similar these Jacobians end up being, just in terms of computing them. You just need to substitute a few things and find a few different derivatives. But alright, so how do we approach this? How do we start finding the Jacobian matrix for this function? Well, let's do a similar thing to what we did before in our practice with Jacobians. So let's make a vector, and kind of so the output of this is going to be a vector. It's going to be some sort of vector because we're taking two vectors, doing something on them, and then outputting a vector. So what is this output going to look like if we're going to display it as a vector of functions? Well, it's going to be some f1 of v, and then some element-wise operation, and then some g1 of w, and then we'll have some f2 of v, and then some element-wise operation, g2 of w. You get the point. This goes down to fn of v, and then some element-wise operation, gn of w. And the reason why we don't index these variables v and w is, as I said, these functions f and g don't necessarily have to be element-wise. So this maybe f2 might use all the variables of v. That's why we don't add some sort of index there, because that's going to limit to only element-wise computation, or like just a single value. But we don't want to do that. We want to let this function be able to compute anything with all the values in this vector. Same thing for all that. But we do index the functions just to organize them better and to be able to calculate the derivatives better with respect to each of these functions. Okay, so awesome. So what we're going to end up with is some Jacobian change in f, change in, let's go with v. So what we're going to do is we're going to, so remember how the rows of a Jacobian deal with, so let's index these functions. So capital F, so just keep track of them. So all of these rows of our Jacobian is going to be the functions, and each column is going to be how that function changes when we change a particular element of v. So let's take the first thing here. So this is going to be f1, and how does f1 change when we change v1, so the first element in v? Well, let's get rid of this. Let's explicitly write out what f1 is going to be. So it's going to be something like this. So, well, it's going to be exactly this, actually. But this will make it a little clearer as to what we're doing. So that's a change in v1, and how does v1 affect the output of this? So let's just keep doing these and write out our whole Jacobian and see if we can find any patterns. So let's go with the change in v2 now, because we're going columns, but we're still dealing with f1. I'm going to run out of space. I always run out of space. Oopsies, I forgot a thing here. V, kind of running out of space. But you get the point. It's going to be all the first functions with respect to different variables. So let's make it general. Let's go to the end. So that's going to be some nth value of v in the vector v. So it's going to be f of 1 still, of v, and then some element-wise operation, and then g1 of running out of space. But you get the point. And then for our second layer, it'll be a change in v1 again, but this time with f2. So now it's going to be this function 2 here. So how does the change in the first element of v1 change this second function here? and g2 is obviously goes down as well. So I'm just going to complete this. And this is just for completion, just to make things obvious. Alright, I might fast forward this in the tape. I might not. I might make you sit through this. Who knows? Blah, 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 and around space. And then for this last row, we're still dealing with the same variables, but now we're dealing with the nth function here. So how does each thing in here, each variable affect the last function? I might be getting sloppy here. F of n, so we're dealing with the nth functions. So this goes on to something like that. Now this is not very neat, but hopefully you get the idea. So basically here, for each row in this Jacobian, we're going to be computing how this variable, v1 and v2, or whatever it is, changes each function. But if we look at this, we can notice some patterns. Say if we take this, right? This should be okay. But let's see why it's okay. So this derivative here, this partial derivative, measures how this first function here changes when we change the first element of v1. Now, in our case, when we're dealing with things like Hadamard products and things where g and f don't manipulate anything, we can kind of just ignore g and f because they're constant functions. So let's not worry about that. So for example, let's get rid of f1 and g1. So we're just left with this. So this is going to be fine, because this is an element-wise product. So we are dealing with the first element of v and the first element of w. Because in this first row here, that's what we're doing. We're dealing with the first element of this vector, so that simplifies down just to v, and the first element of this one, which just simplifies down to w. So v1 is going to be okay, because there will be a change. When we change v1, it will change the output of this, because we're doing computation with the first variable of v and the first variable of w. But let's look at something like this. So this will be a non-zero number, but let's look at something like this. This is measuring the change when we change v1, so still the first element in the vector, but when we change the second function. And the second function, if we look at it in the same way, still deals with the second values in v and the second value in w. But we're taking the derivative with respect to the first value in w, and v, sorry. So there's going to be no effect, because v1 doesn't play any effect on this element-wise operation, but this is an element-wise operation between v2 and w2. So this element, so this goes to 0. I need water, but I'm going to finish this soon. So this evaluates to 0, because there's no effect. v1 has no effect on the second function. So does here, because v1 doesn't have effect on the third function, because the third function deals with v3 and w3. So this becomes 0 as well. And then looking over here as well, the second v, so the second element in v, has no effect on f1, which is what we're dealing with here. Because f1 deals with v1 and w1, not v2 in any way. So this equals 0. So what we're going to see is we're going to see this pattern. We're going to see anything off the diagonal will turn into a 0. So we're just going to get this diagonal matrix of non-zero values, and everything off there is going to be 0. Need water. But the thing that we want to mention, and the thing that I want to mention, that I want to really make clear, so seeing from that and extrapolating that to all sorts of non-zero numbers, this isn't even water, this is coffee, but that helps. So one thing we can extrapolate from this is that for all element-wise functions, the Jacobian will be diagonal, because we're going to be dealing with only some v-nth with some w-nth component at each function. So if we're taking the derivative to something that's not the v-nth or w-nth component, there's going to be no effect on that function. So for any element-wise function, we're going to get a diagonal Jacobian matrix. So let me write that down. That's important enough to write down. The Jacobian of all element-wise functions are diagonal, and that's a big thing, and that's really, if you're thinking computational-wise, computing, so I'm not going to erase that just yet, but if you think of that computational-wise, that's a lot cheaper than computing an entire Jacobian matrix, because you're just dealing with the diagonals. And a common way to write this is diag, short for diagonal, obviously, and then all your diagonal non-zero values. So if you had some sort of diagonal matrix like A, B, C, then you would have diag A, B, C. And then this would say that, oh yeah, it's A in this place, B in this place, C in this place, and everything else is 0. It kind of almost multiplies these values by an identity matrix. So that's important to note. And then once we move on to the actual the product, the element-wise product, this will be a lot easier to understand, because the element-wise product actually is obviously an element-wise binary function. So that'll make deriving that a lot easier. So I'm going to get some water, and we'll talk about the Hadamard product and deriving that, as well as how to derive a sum, because that's basically all the operations in a neuron, and then we can get to actually deriving a neuron's bias and weight. So, yeah, is there anything else to mention? I don't think so. But that's pretty incredible, and let's get to the next thing. I'm going to get some water. Alright, so let's just quickly talk about the derivative of a Hadamard product. This is actually going to be a pretty quick discussion, since we already covered the derivatives of binary element-wise functions, and the Hadamard product is a great example of a binary element-wise function. So the Hadamard product, I already mentioned what it does. It element-wise multiplies two vectors. So how do we take the derivative of this with respect to the elements of either W or V? So let's just quickly write this out. So our function capital F takes some vector V, some vector W, and returns to us some F. So just keeping the notation until I prove that you really don't need notation in a Hadamard product. You really don't need the functions, the mini functions. G1 of some W, and then some F2 of some W, V, and then some G2 of some W. This goes on, some Fn of V, and then some Gn of W. Okay. So the reason why in a Hadamard product you have some W and some V, and you're multiplying them. You don't do anything to the vectors before you multiply them, because, especially in our case, when we're thinking of Hadamard products in the context of substituting for a dot product, we're kind of just breaking a dot product down to a Hadamard product and a sum. So we aren't multiplying anything because we're trying to mimic a dot product. So in that case, we don't need these little functions, because we don't do anything with the vectors, we just take them in. But the thing is that before, when he did have these little vectors, we never really put it down, but we would technically be indexing the output of this little function here, because it's still element-wise. So even though these functions are not element-wise, this little mini one, it still needs to be element-wise these two. So this is like this is the nth row of this output vector. So this is Fn, f of Vn, so it's the output of f of V, and then the nth index of that, and then it's the output of some G of W, and then the nth component in the output of this, and then we're comparing those element-wise. But now that we don't have that mini function around it, we just assume that we're dealing with the Vnth and the Wnth component of our input vectors, because we don't have that function anymore, so we can put our notation on these. So you'll see this will just end up being this. Okay, so that's simple. So now looking at our Jacobian for something like this, with respect to v, let's keep respect to v. So it's going to be some, I'm not going to write out the whole thing, but I'm going to say some v1. Also this is 1. So that's going to be that, and that's going to be some vn. This is going to be f2 now, v1, and then let's just make that, and then some f2, sorry, and then to some v2, sorry, and then we have this going down to some fn. Awesome. Alright, so now that we have this, just looking at each of these, and these are going to be now products, because this is specifically the Hadamard product. So for each of these, so how does the first function change with respect to v1? Well, it's going to change by a factor of w1, because you're going to just be multiplying these. So just think of these actually just as multiplications, because you're already looking at this element and this element, so it's already an element-wise, so it's just a multiplication of the first element of this and the first element of this, the second element of this and the second element of this. So they're just going to be multiplications, and when you're deriving a multiplication, or differentiating a multiplication, and if you're differentiating with respect to x, and you have some xw, with respect to x, it's going to be w, right? So it's going to be the exact same thing. So this is going to be w1, and again, this is going to be a 0. I don't think you need me to fact check that anymore. Anything off the diagonals of an element-wise function is going to be 0. So we're just going to end up with this. It's just going to be some w2, and this is all going to go down to some wn. So same thing around if you took it with respect to w1, so this will be v's instead. So if you took it with respect to w, these would be v's. But it'd be the exact same thing. And then that's pretty easy to kind of believe yourself. But yeah, I just want to cover the derivative of a Hadamard product. So that means we are about halfway to deriving a neuron, because we just need to cover the sum now, and we need to cover one thing called scalar expansion, or deriving scalar expansion, which I'll go into right after this. Alright, see you there. With the derivative of binary operations, we can deal with the two slightly easier ones. One that I forgot to write down on the previous one, but kind of came up to me, was the derivative of a scalar expansion, which basically means the derivative of multiplying a scalar by a vector. Again, all of this was kind of inspired by Jeremy Howard's and Terence Parr's paper on matrix calculus, but that's mostly just for the initial kind of information, and I'll be adding more on with regards to backpropagation later. But this is just to get the kind of groundwork done. Alright, so scalar expansion. So let's deal with scalar expansion first. So scalar expansion is when you multiply some maybe 2 times a vector, v. Actually, let's write down the elements. So the result should be familiar is something like 2v, like this. We just multiply every element by this, or we can add every element to this, or we can divide every. So I guess it's, so what you can think about it is and what is actually going on and what happens in any sort of computer program is that we broadcast this scalar, so it's called a scalar expansion because we expand it to be a vector of the same size. So something like this. And then we just do an element-wise operation. So that's the exact same thing as just multiplying by a scalar. But we never actually technically multiply by a scalar. We always kind of under the hood, it's broadcasted into being a scalar of the same size. So what's the derivative of something like this, a scalar expansion, or both the scalar expansion and the execution? So what's the derivative with respect to v, the elements of v, and and more interestingly, and more new, I guess, is what is the derivative with respect to that z that we multiply or add to each element? Well, we can view this in similar terms. So remember how before we had some f of x, some v and then w. So now we're only taking one vector and some scalar x, right? So then our output is, so we can keep this kind of function. Oh, let's keep this capital. So we can make this some function of our vector, and then some element-wise operation, and then g of our scalar x, where this function g of x equals the ones vector times our scalar x. So if you're not sure what this means, this g of x is expanding this x into a vector. By multiplying something by the ones vector, you just, so if it's 2 and 1, 1, 1, this just becomes 2, 2, 2. Alright. So that's kind of the mini function there. So this is a case where that mini function inside of the bigger function is actually helpful. So, alright, so we can do the exact same thing as before, where we can represent this as a vector function. So we can make it some f1 of v, and then some element-wise operation, and then g1, oopsies, g1, it's not pretty, g1 of x, and then f2 of v, some operation, g2 of x, bang, 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 fn, v this, and that's some element-wise thing, and then n of x. Awesome. Okay, so now that we have that, so this is our function, this is the output, whatever it may be, it's going to be a single vector. So, first of all, just to kind of imagine, I guess, in our head, or we can write it out a little bit, what the Jacobian is relative to, with respect to the elements of V. So what f of V looks like. Looks relatively similar. So we're going to be taking the elements of, so it'll be, I won't write out the full thing this time, so we're just going to say f1 with respect to v1, and then f1 with respect to v2, just dot dot dot, and then f1 with respect to, vn, and then we're going to have some f2 with respect to v1, some f2 with respect to v2, and that goes on, and then this goes on downwards, so that's going to be some fn with respect to v1, some fn with respect to some v2, and this goes on to some fn with respect to some vn. Okay, so this is going to be our Jacobian matrix, but what are these going to actually look like? So what is our, how does our vector, the first element in our vector 1 change the output of f1? Well, it's kind of the exact same as it was before. Like, it'll be some sort of non-zero changing thing. It depends on the operation. But if you were to say maybe in multiplication, and if you're saying that this f1 doesn't do anything, so it's a constant, it would be, yes, it would be x. Because you would multiply, so you just end up with this vector, and then you can think of, now that you're getting rid of this f, you can confirm that that's the first element of v1, because the only reason we didn't index these, as I was saying before, is because this f might deal with multiple variables, but now that we have no function, that we have to make it the first element of v1, because before it was the fact that we could have some v and then like this, and then we would be indexing technically the entire vector, but now that that's gone, we can just say v1, and then some sort of, and then, well, this is still important actually, because this actually does something. So it'll be some v1, and then times this scalar, because this vector is just going to be a vector where every single element is the same. It's going to be x. So this scalar product is just going to be v1 times x, so that's going to be, what is that going to be? Well, that's just going to be x. So we're going to see the same thing. We're going to see a diagonal Jacobian matrix once again, and we're going to see, obviously, v1 has no change on v2, so we're going to see these become zeros. So with respect to v, we're just going to get whatever the scalar thing is for a multiplication. We're going to see something like this, and yes, that's it. That's it for the v with respect to the v's. So now we're going to think of something a little more interesting, or a little more new at least, is the derivative with respect to x. So x is unique in a sense that x is a scalar. X doesn't have any indexes because it's just a single number. So all we can do is see how this scalar changes things in each of our functions, f1, f2, etc. Because it's not, you can't go horizontal, because horizontal along the Jacobian means that you're indexing into a vector, because it's going to be some v1, v2, blah blah blah, but x doesn't have any indexes. So all you can do is go down and see how x changes the different functions. So when we're taking the derivative with respect to x, what we're going to get is a gradient and not a Jacobian, because we're going to get something diagonal. And when you think about it, this makes sense, because when you're doing a gradient, when you have a gradient, that means you're dealing with something that inputs a scalar and outputs inputs a vector and takes out a scalar. And now, essentially, what you're doing by taking the derivative with respect to the scalar, you're doing kind of that sort of thing, because you're kind of disregarding how this affects it. So we're doing, so we're going to get a gradient. So we're going to get some sort of gradient of f with respect to x. So we're going to get how f1 changes with respect to x, how f2 changes with respect to x, and all the way down to how fn changes with respect to x. And in this case, if we continue with our multiplication, that's just going to be v1, v2, and vn, just by using, simple scalar calculus rules. Because this will be some number, and then we're going to be multiplying by this, so it's going to be, we're just going to eliminate that, and we're just going to get this. So, simple enough. So the vector of, the gradient of, with respect to x, is just going to be a vector of the v1. So it's actually going to be equivalent to v, but it won't always be. So if it's a plus, it'll actually just be a vector of 1s, because you're just going to be, when you're doing a scalar derivative and you just have one of your own variable, it simplifies to 1. So same thing here. So that'll be just 1s. If it was a element-wise subtraction, then it'd be negative 1s. I'm trying to think, is there any other differential things that are kind of interesting? Not really. But yeah, so that's just, you get the idea. So that's a scalar expansion. Next up we'll talk about sum. Alright, so now we're done with the hard part, which was differentiating a Hadamard product or a binary element-wise function. Now we have something easy. We're differentiating a sum. So what is the function that we're kind of trying to differentiate here? It's something that takes a vector v and sums over the elements all the way up to vn. So really what our function looks like is the summation, it's an ugly summation, is up to n, starting at 1, and then some g of v. So the reason why we use g again is very much similar to our element-wise products. It's that we might want to do something to each value of v that might not necessarily be element-wise. That's why we're not indexing the v, we're indexing the function. In my opinion, an almost better way to show this would be something like this. So you might want to think about it like that. So example of a g would be, maybe we want to multiply each element by 2 before we add it. So let's say that's our thing, so we just multiply by 2. So that means this will get a vector like this. So each of those is a 2. And then we index into the ith value of this new vector. The reason why we don't put something in here is because, similar, again, we might have a function here that doesn't, so we'd be indexing into that vector. Whatever it is, we're indexing into this kind of new vector. You can think of it like that. Anyway, so what is the derivative of this summation function with respect to each of the elements? So how does each element in the vector change the overall summation? So how does changing each element change the overall result? That's what we're asking here. So now with Jacobians, we used to have things where we have multiple functions, so each row is a function. But in a summation, we only have one. We have the summation. So now we're going to have one row. And when you're thinking about it, a summation is a vector to a scalar function. We're taking a vector and we're summing over and we're getting a scalar. So it makes sense that it's something like a gradient, not a Jacobian. So what we're going to do is we're going to have a single function, which is the summation s, we'll say the function summation. And each element here is going to be the summation with respect to a variable in the vector. So let's just write this out to make it concrete. So the derivative of s with respect to some v1, derivative of s with some v2, oopsies, all the way to some vn. So actually expanding this, or expanding the s, what we get is something like this. Try to write this out as fast as I can. So this GI is always going to be the same. Obviously, because we're in one single row. We could index it as G1, or we could just index it as G. That might be the best way to go. But we do want to sum over it, so not really, actually. Let's keep this I. And this is obviously the same summation over I. I just don't want to write it all the same. And then we end up with Vn over G. Okay. Well, from here we can take the rule that the derivative of a sum is the same as the sum of the derivatives, so we can just swap around the order of these. So we can put the thing out here, and then we can just put our derivatives in here. And soon enough this will reveal something interesting. Completely forgot to do the summation on that one, I just realized. Okay. So now that we have this. So looking at this, right, so when we're taking the derivative with respect to v1 over, so let's first consider the case where g is constant. So g is just nothing. So g of v equals v. So there's no change. Let's consider that. So just a pure summation. In that case, we're not going to have any of these g's. And we're just going to have this. So, and now we're going to have a vi, because now we won't be indexing those functions anymore. So now what we're going to have is that the derivative will be 0 on each summation until that this I equals 1. Then it'll be 1. So basically, in this summation, we're going to go through I equals 1. And that'll be, 1, because then this will be v1, and the derivative of v1 with respect to v1 is 1. But then it'll become I equals 2, so this will be 2, so it'll be plus 0, all the way until n. So the result of this would just be 1. This will be 1 plus n minus 1 zeros, pretty much. So again here, right, so when I equals 1, then this will be 0. But then when I equals 2, then this will be v2 with respect to v2, which will be 1. And it'll be 0 for the rest of until n. So this will be 1 again. So I might be seeing a pattern here. The entries of this gradient are just going to be all 1s. And if we have some g, for example, if we have some g that multiplies, so some z, that multiplies each thing by z, well then it's just going to be z1 plus z times 0 times plus z times 0 times plus z times 0, so it's just going to be z. So if we have some function g that multiplies each thing by some scalar z, then our output is just going to be this. So you can see that the outputs of a summation are usually, if we don't have any g, just 1, the 1's vector, transposed. Or it might be some z times the transpose 1 vector. Or it might be some other element-wise operation that we do on each scalar. So that's the derivative of the sum. Pretty easy stuff. Alright, so I'll see you in the next time. We covered all the sums, So what we're going to go into now is actually deriving a neuron with respect to the bias and the weight, so that's going to be exciting. Alright, see you there. Okay, so now this is exciting. Now we're dealing with neurons, and we're trying to take the derivatives of neurons with respect to the weight and the bias. So let's take our running example. And what we're going to do now is we're not going to worry about the cost function just yet. We're just going to find how the activation of this one node changes when we change the weights and the one bias of the system. So there's 6 things that we can tweak, and then we're trying to find basically the gradient with respect to all the weights and the bias. So what we're going to do here. So let's write out the notation of this single neuron and how it processes things. So it's going to be something like this, right? So it's going to be a W transpose X plus B, and then that's going to be what our activation is equal to. So we can do some kind of, so basically this is something that you would use the chain rule on, because you have this function here and you have this function inside. So if you're trying to take derivatives with respect to W or B, you can't just go straight from A to W. You need to deal with this intermediate activation function. So you can do some kind of chain rule investigative work where you can say, okay, the change in A with respect to, let's say W, we also want to do B as well, is equal to, we can't go straight to W because there's something in between, there's this function. So we can say, well, this inside is Z, right? So we can change this to the change in A when we change Z, which works, because then that's going to be basically the ReLU thing. Or the activation function, depends which one you're using. And how does D change when you change the bias? I mean, the weight. Over here it's the bias. Okay, so perfect. So that's kind of what we're looking for. So how can we use what we used before to, how can we use what we learned to differentiate this? So you have all the tools we need. Well, remember how we separated a dot product into a Hadamard product and a sum. So what we can do now is we can just kind of rewrite this as this new funky thing. So now we're going to write sum of W Hadamard product of X plus B. That's exactly equivalent. So now we have a couple more layers in our chain rule thing, because now we have another function. So let's say that this inner thing here, the Hadamard product, is going to be H, and this thing here is going to be S of H. Perfect, so it's the sum of H, so now it's going to be, how does Z change when we change this sum? How does this sum change when we change this H? And how does H change when we change our X? W, sorry. So we're adding a few more layers onto this. Same thing here. Actually, not different thing here. This one we can still go straight, because this bias is completely independent from all of this. So when we're trying to take a derivative with respect to B, this just kind of all zeroes out, but there's no B related to any of this. Alright, so these are the 2 chain rule things that we kind of need to figure out. So we already know how to do most of this. So in general, how does the Hadamard product change when we change one of the multipliers in the Hadamard product? Well, it just becomes, remember, our Jacobian is just a diagonal matrix of the elements of the other vectors. So it's going to be x1, x2, xn, and these are all going to be zeros in our Hadamard product. Obviously I won't explain why, because I already did, so alright, so that's going to be what this is, right? We got that covered, so let's actually label this accordingly. Alright, so we got that covered, so we can also show that as diag of x1 all the way to xn, and that's kind of what we're going to be using. And I'll just treat it like a vector, right? A horizontal vector, or a vertical vector, just a vector. We can treat it almost as a vector because all the information will be stored in a vector. So now how does the sum change when we change h? So this is why I meant you should probably think of this as a vector, because now we're going to be summing over all the elements in this. So we can kind of think about it as summing over all the elements in this diagonal vector. So since the sum isn't anything fancy, we're not multiplying anything, we're not like doing that, So remember we had that g in there something, that's going to just be a constant function. So it's just going to be 1 transpose, because that's going to be the output derivative of our sum when we don't have any g. So far, our derivative of s with respect to h is just the horizontal 1's vector. So let's just take our time to replace these. Sorry, I should multiply this by diagonal. Okay, so now we have to worry about this. How does this z change when we change s? Well, that's not too bad, because this s is just, so that's just basically s of h plus b. So it's 1. Right, because we're trying to find s of h with respect to this thing, right? So that really doesn't add anything. Alright, so, yeah, because this b zeroes out, and then we found an s of h, so this just becomes 0. Yeah, just confirming that. So now we have one more interesting thing here. And first of all, let's multiply this out. So this is going to be a horizontal 1's vector, basically multiplied by another vector of just the values of x. So this is going to become a horizontal x vector. So it's basically going to look like this. That's what it's going to look like. But I'll just write out x transpose. And this 1 can go away as well, so let's just move this whole thing. And now here's something interesting. So now we're dealing with this activation function. And obviously this activation function can be a lot of different activation functions. Depends. It could be tan h, or ReLU, or sigmoid, or any kind of one of the many versions of sigmoid that exist now. But let's just stick with ReLU because it's one of the more popular ones. And also, if you're reading the paper that I've mentioned a couple of times by Terence Parr and Jeremy Howard, they also use ReLU, so you might be able to follow along a little better if you're using that paper as a secondary reference. So let's use ReLU. So the funny thing with ReLU is that so as opposed to sigmoid, which is a concrete function, I don't remember the exact sigmoid function, but it's it's an exact function. The function for ReLU is a bit weird. It's the max of 0 or z, where z is this. So basically, looking at the graph where this is z and this is the output of ReLU, I don't know how to put that, but well, ReLU of z, yeah. So it looks like this. So basically, any 0 that is less than 0, any z that's less than 0 is just clipped to 0. It doesn't stay negative, it just gets clipped to 0. And anything that's non-negative, so above 0, is just itself. So its derivative stays the same. So it's just 1 times its derivative up until that point. Whatever that is. So with that, how can we take the derivative of something like this? And also, one more thing, just to mention that the derivative is actually, the function of ReLU is actually not continuous the whole way through, because it's not differentiable at this exact point here, right at z equals 0, because as you might know from like Calculus 1, the derivative at like sharp turning points is undefined. You can't do it. So it's actually undefined at this point. But this is solved really easily in many computer programs. Well, first of all, getting an exact 0, like a 0.0000 in anything is extremely rare. But if you did happen to do that, the computer would just add a really small, like, epsilon, which would be like maybe 0.000001, right? So just to make sure that doesn't happen. So it really doesn't matter in practice. So how do we take the derivative of a max? Well, it's actually not that hard. What we do is we actually take a piecewise function almost. So we make 2 scenarios. So if z is less than or equal to 0, sorry, and then we have another circumstance where if z is greater than 0, so it's the kind of nice case. So what do we know now? Well, if z is is less than 0 or equal to 0, then it's going to zero out everything. Our entire derivative is going to become 0, because just think of our chain rule thing. This is going to equal out to 0, so it's just going to get rid of everything else. So this here, this x transpose, oh, that's kind of confusing. This x transpose is basically, we multiplied, you remember there's like 3 derivatives here, and we multiplied and we combined into this thing. So this represents how z changes with respect to w. So up until that point, it's going to be 0 times this. Right? So if z is less than 0, then it zeroes out everything. But if z is greater than 0, then it just keeps it the same. So it's be 1 times this. So now we can do some substitution. So this will just equal 0. So that will just equal 0. But then we can substitute this. So this is going to be x transpose. Actually, that transpose comes from that. Alright, so, and then we can substitute the z as well. So what is this z actually? I won't put this Hadamard product thing because it's just a little messy, so I'll just say if w transpose x plus b is less than or equal to 0, or if w transpose x is greater than 0, and that's it. That's how the activation is changed by w. So now that we have that, we just have to do the bias, which is a lot easier. So the bias on the other hand, I'll do it right above. So just to kind of complete this bit, this tells you that for some specific w, how much it changes with respect to whatever this is. So this will end up being a gradient with something like, it's a bit weird because the piecewise function, but this just accurately tells you what happens with regards to any w. So let's just deal with biases now. So a bias is just these two terms. It's how z changes with b, and looking at, if you can remember what this looks like, I'm just going to rewrite it really quickly. So that's going to be it. So the b, so how z changes, so this is z, how z changes with respect to b is just 1, because there's this cancels out to 0, so it'd be 0 plus 1. So the first part is going to be 1. So that's easy so far. And then we just use the same piecewise trick here, because now we're taking a to z, so it'll be this. I don't know why I'm putting max here, it's really just this. It's that our a with respect to w equals this, or a with respect to w equals this. This will be b. So it'll be 0 times this, so 0 times 1 if w transpose x plus b is less than or equal to 0, and it'll be 1 if this will be 1 times 1, so 1 times 1 if w transpose x plus b is larger than 0. So we can just apply that to 1, and so that is 0. So that's a lot simpler. So I just made this one mistake that I just want to take note of. It's not too big, but it's important to take note of. So back here, remember when we weren't really all the way done yet, we had here that 1 times, well, I'll just rewrite it. Remember how this 1 times the change in, what was it? Change in z when we changed w. And then over here we had 0 times the change in v when we changed w. Well, the thing is that this is x transpose, right? And that just equals x transpose, and we got that. But the thing is that this also multiplies by x transpose. So this actually becomes a vector of zeros transpose. So I just want to make that clear. So this is going to be the entire vector x, and this is going to be the entire vector 0. So that makes a little more sense when looking at the overall gradients of these functions, because if w transpose x plus b equals is 0 or less for some certain activation, then the derivative with respect to every weight will be 0, because it'll all be zeroed out by the by ReLU. But if w transpose x plus b is larger than 0, then the derivative with respect to each weight will be its corresponding x, funnily enough. So for example, it would look like this. So if you wanted to find, oh, how does the activation change when we change, say, example, weight 4, it changes it by this amount. That's the multiplier, I guess. You could say that. So that's the derivative. So for example, this x4 is the derivative of the activation with respect to the fourth weight. And if it's all zeros, because it's been zeroed out by ReLU, then the fourth weight has the derivative 0. So I just wanted to mention that. And also I want to apologize for this kind of weird vector notation here. That was kind of wrong. But I hope you kind of got the point. Alright, so next on I'm going to move on to adding on the cost function and seeing how we can take the derivatives with respect to the cost function, and then exploring how we can use those derivatives to do gradient descent and find the optimal solutions. Alright, see you there. Alright, so now that we're moving on to not just dealing with the derivatives of the activation with respect to the weights and the biases, but now we're dealing with the cost with respect to the weights and the biases. So continuing with our example, now we're going to have just one more derivative in our chain of derivatives. So this is going to become an activation, and then we can compare this activation against the real total cost using the mean squared error function, which I'll keep over here. So our cost function, not to forget it, is 1 over 2m, and then summing over all our training examples, and I'll shortly explain how we're going to represent training examples. Sorry, I equals 1, and then all the way up to m, and then the order doesn't really matter because we're squaring it, so I think I might have said before we're going to take our prediction and subtract the actual answer. For now, just for ease of derivation, I'm going to switch it around, so I'm going to take the actual answer minus the predicted answer activation. So let's just kind of set that as activation, and then we square that. Okay, so that's going to be our MSE. So that's going to be our cost function that we're going to be using. Just keep that in mind. So anyway, so now we calculated in the last part how A changes when you change the weight and the bias. So we're more than halfway there. Because if we think about it, it's just, we have this chain of derivatives that we use the chain rule to compute, and we just have to add one more kind of link to that chain, which is that link between A and C. So our goal is to find how C changes to W as well as how C changes to B. So we can do that. We calculated in the last part how A changes when we change W, and how A changes when we change B. And there were those weird piecewise things where we get a 0 transpose vector if W transpose X plus B is less than or equal to 0, and then we get exactly the derivative. So how W changes when we change how Z changes when we change W if W transpose X plus B is greater than 0. And then similarly for the bias, we also have this weird piecewise thing where it's just 0, a scalar if W transpose X plus B is less than 0, and it's 1 if W transpose X plus B is bigger than 0. So we have those two weird piecewise things that are that represent this. So we are already halfway through the battle, because we already have that part that connects the W, and that's kind of the hardest part, because like if you think about it as a chain, almost as like a chain, like literally the chain rule, by figuring out how A relates to W, we had to go through this whole bunch of derivatives. So let's say how A relates to W, we had to go through all of these, these different chains. Like we first connected A to W, and then we connected W to, so we had to first connect how A changed with Z, and then we had to change how Z changed with that weird summation thing, and then we had to check how that weird summation thing went to our H. So you can think of it almost as a chain, literally. But we've kind of figured out most of this chain, because we figured out directly how how A, our activation, changes with W and B. So now we just have to add one more thing to our chain. So this brings us almost all the way here, this thing we already figured out. But now we need to connect that with the cost. We just need to make this one last link in the chain. So what we can do is we can say, we can do this thing. So we can say the cost changes with A, and looking at we want always the same terms across, and that works out. So this is the only thing that we don't know that we need to find out, is how the cost changes when we change the activation. So looking at our mean squared error, this means that we have to take the derivative of our mean squared error with respect to our activation here. So that might look tricky. It's not too super tricky, it's just a bit tedious. And then similarly with the bias, we have to figure out how C changes with A exactly in the same way, and then we just use the other piecewise function, and then we get the exact same thing. So that's all we have to figure out, this one derivative. So how this changes with respect to the activation. So let's see if we can do that. I might have to look at my notes because it's a pretty long process. Again, this kind of pairs with that paper I've been referencing by Howard and Parr. Okay, let's see if I can have space to keep that up there. I'm going to try. I'm going to probably run out of space enough to rearrange, and you get it. But okay, so let's just write out our... just the thing, I think in Howard and Parr's paper, they didn't use the 2m. I think they just used m, I think. But I'm going to just stick with 2m because it's kind of what I'm more comfortable with. And I think it works out nicely because you factor out that 2, as you'll see. So then we sum over this. Equals 1. So, oh yeah, one last thing I just want to mention before going into this is how we express our training examples now. Because as you notice, now we're as part of our cost function, we're summing over training examples. Because this m is how many training examples we have. So for each training example, we're taking the error and then we're averaging it out for a total error across our training examples. So how we're just going to represent this is before we had we just had one training example, and that was a vector that goes from this down to xn. So now we're just going to extend this into a matrix where each column is a new training example. And then I guess I'll signify this with the training example I put in the superscript, and then the variable number I'll put in the subscript, but I really won't be using individual variables that much. I'll just be kind of referring to it as a matrix. And this matrix with the training examples as its columns and the variables as its rows, I will signify that with capital X. And this doesn't need any superscripts, subscripts, it's just the single input. Alright, so just let's get that out of the way. Alright, so we have this error. So we have our actual answers y, so each column of our x associates with a right answer y. So each of our training examples has like a right answer, because this is, supervised learning. So minus our activation. So I'm not necessarily sure what I should use for the activation. I'm just going to say, so this is our final activation. Well, in our simple neural network, it's the only activation, but in a larger neural network, as we'll explore right after this, with multiple layers, it would be AL, but I guess we might as well get used to that notation. So let's say AL is the output of our neural network that we're going to be comparing against the true answer. And then we square that cost. So let's take some derivatives. So is there anything that we can kind of simplify beforehand? So we already know that, we already know all this. We already know everything like this. So we can take one more thing out of this to kind of simplify it a little more. So remember with the chain rule, we're always trying to find intermediate functions and trying to simplify things. Well, this here is a pretty good candidate for something that we can kind of simplify. Let's say that y minus al equals v. Yeah, so this isn't super tough to get the derivative of. So really all we're doing is we want to take the derivative of all of these with respect to the weight, since that's just the nature of the chain rule. We can't go like halfway. We want to be taking this with respect to the weight. So if we're going to make this equal to v, we want to kind of, because we already have a with respect to w, so we're kind of going outwards, if you would say. We're getting closer to the cost, so we need to find something in between the cost with respect to a, so we're kind of finding a root in between here. So now, since assigning this little v thing here, basically we're adding another link in our chain. Basically what we're doing is we're changing this from how a changes from w, and then we're seeing how v changes when we change a, and then we're making this how c changes when we change v. So you see how we kind of added another link in our chain by adding this new variable here that represents this. So now we see that this is just v squared, which is actually a lot nicer to look at. But we kind of had to sacrifice by finding another derivative. But this one isn't super hard to find. So now that, I'll just rewrite this in a kind of a nicer way. So we're trying to find the derivative of c with respect to w, and then now we've added this new thing. So we're trying to find how c acts with v, and we're seeing that v acts with a, and how a acts with w. And we already have this. So we can collapse this into how v changes with w. So that means we have to find, of this, we need to find the derivative of this v with respect to w. So we're going to take the derivative of this with respect to w. And what's that going to give us? Well, this y is completely unrelated, so that just becomes a 0 vector. And then this is going to become minus al. And using the chain rule, that this al with respect to w is just going to be minus of a over w. So this is it. So basically this equals that. Pretty simple stuff. So how v changes with respect to a is equal to how a respects to w, just with a minus now. So that's important to note. So let's put that down somewhere. Let's put it down right here. So how v changes with respect to w equals minus how a changes in respect to w. Alright, so that's good to think about, and then we'll explore what it means to take the minus of a piecewise function later on. It's really not as hard as you would think it is. So we have this now. We have this slightly simplified function now. So now all we're trying to find is how c changes with respect to v. So what does this look like now? So let's go to the next step. So let's actually start computing this thing. So we're going to now try to find how it goes with w still, but it's just a little easier. Just writing this out in a nicer fashion. So that's what we're trying to do. Okay, so let's go to the next step. So we know that the derivative of a sum is the same as the sum of the derivatives, and this right here is just a number, so we can just take that out. So we can say 1 over 2m, and then sum over m, and then I equals 1. And now we can move this in here. Okay. So now, taking the derivative of this is going to be pretty easy, pretty trivial. So let's then do that. Because we already have this. So this of that squared is just going to be, so now we're going to just have one more chain in there, but this is going to be a super insignificant chain because it's just using the power rule once. So if you see that right now we have v of w, we have what that is. So to find what v squared of w is just another chain rule thing. So we need to find the derivative of v with respect to w, which we already have, but then we need to find the derivative of v squared, which would just be 2v. So we need to find both the derivative of v with respect to w and the derivative of v squared with respect to v, because it's like a chain rule thing. It's just simple chain rule. So we can just do that. So just to display what I mean, all I have to do is just this. And then this is going to be this. So this is what we're doing now. So kind of just to take the derivative of this, we already have how v changes with respect to w, but v squared is kind of another function outside of that, so we have to take the outer function, so it's going to be how v changes with respect to, how v squared changes with respect to v, and then how v changes with respect to w. So just using the chain rule to explain that. So this is easy, this will be 2v, and then, yes, and then this will be, we'll just keep that like that for now, because we know that expanding this out is going to be kind of a pain, because it'll be all of this, so let's just keep that unexpanded for now. And see if we can do anything before expanding that out. Okay, well, one thing we can do is we can take out this 2v. I just forgot that one over 2m. So we can actually take out that 2v. Well, we can take out 2, and then that'll cancel that out. Nice. So we have this now. So this is looking a lot nicer. So let's replace this quantity now. Finally, we're going to bite the bullet and do that. So what is this going to look like? Also, we're going to tackle this problem of what does the negative of this look like. So let's just take it with respect to the weights first, because those are arguably a little more important. So let's just replace that up here. So 1 over m I equals 1. Let's write this nice and pretty. So now we multiply v times, so when you take the negative of a piecewise function like here, all you do is you make the options negative. And when you think about that, that makes sense, because if you're in a piecewise function and the piecewise function decides, depending on these circumstances, that you go this route, it's no longer a piecewise function. You see, like, it's only a piecewise function to us because, like, it's like, oh, it could be this, it could be this, but if you are less than 0, it's simply this. So it'll just be negative that. And if you're looking at this, it'll just simply just be that. So you're going to have to take the negative of that. It's like, it's something special. It's just like a kind of an if or an or for us to look at, but for the actual numbers themselves, it'll just be like going through this one or going through this one. They don't need to do any thinking or anything like that. So we're just going to take the negatives of the option. So the negative of 0 transpose, which is the 0 transpose, and then the negative of z over w. And then I don't really need to do these. You're probably tired of these, but, you know, it's good to be thorough. So I did that. There. Alright, so this is what we have so far. So all we can do is we can actually multiply this in, and again, using that same kind of intuition that a piecewise function isn't really a piecewise function to the numbers themselves, we can just multiply that in. So v times that equals 0, and I'm just going to get rid of that because it's all going to be 0 anyways. And then this is going to become minus v times that. Alright, so all we do now is we substitute, really. Now it's just a game of substitution. So we rewrite all this, but this stays the same. And then now we substitute this derivative here for the actual derivative, which is x transpose. And then we have this v here. And remember, we assigned this v to the y minus the al. So we're going to have to expand that out, and we're going to have to expand this al too, which is the w transpose x plus b thing, and then it to expand all that out, and then, you know, you see where this is going. So, alright, so let's further expand this out. We multiplied the v in, so that's all good. Yes, so let's now expand this x transpose thing. So now it's going to be vx transpose, and then I'll just do that now. You know the options, right? And then let's go back up here and then expand out this v. Oops, forgot my thing. So now it's going to be on this side it's still going to be 0, but here it's going to be vx transpose, negative v to x transpose. So if we pull that out, so v is obviously going to be y minus al, and then it's going to be times x transpose. Just temporarily, and if you're okay with this, let me get rid of this mean squared error, because I think we got that down by now. So what we can do is this sigmoid here, we're using the ReLU, right? So what this really is max of, oh, that's kind of too close, is max of 0 or W transpose X plus B, because this is Z. So what we can do is, okay, let's just try replacing it just to see what happens. So this A of L becomes this, so minus max of 0 W transpose X plus B, and then X transpose. And then we have our, I'm not sure if I did that right. Yeah, I did that right. Okay, and then we have our, actually this minus only applies to this part. So I think 1, 2, 3 we're missing lots of brackets. There we go. So then we got that. So this X transpose is by itself. It's not affected by this minus directly. And then, so then we still have our W transpose X plus B is greater than 0. So these will come in handy now. You might think I've been wasting time on these, but these are about to come handy. So when we look at this, taking the max of 0 or W transpose X plus B, if W transpose X plus B is less than 0, it would have been handled by this piecewise function anyways. You see, there's no reason to have this max here, because if it chose this option, W transpose X plus B is greater than 0. So this max function is kind of redundant, because this piecewise function does the exact same thing. So we can actually get rid of this max and get rid of this 0, and just kind of take it as this option means W transpose X is already bigger. So we can just do this. And then this, get rid of this. Nice. So we simplified a lot. So this is a lot prettier. Now we can just do the fun little task of carrying this minus sign over, so that's going to become, I don't trust myself on this one, let's say minus 1, that becomes a plus there, so everything in here stays a plus. So we can rearrange that in kind of a nicer manner, so W transpose X plus B minus Y times XT, so that can be your final answer there, so we can replace that with here. So we can replace this, which was W transpose X plus B minus Y, and then this X transpose is still on the outside. And then one last thing that we can do is we can actually bring this summation inside, and obviously summing over this doesn't make sense because we'll just end up with 0 anyways. You'll actually end up with 0, 0, like actual 0, but let's just keep it like that. So now let's bring this in. The 1 over m stays outside. So now we have our 0 transpose t, and then we have this little summation in here. We just brought this inside. Obviously because we can, because using this exact same kind of idea that the number doesn't care of the piecewise function, it just chooses one of them. It's the same thing. It doesn't matter if it's outside the piecewise function. It's the exact same thing. So then we can sum over this. And then we're done. So that's the derivation of the cost function with respect to the weights. And I'll explain shortly what this actually means, because it might seem a little abstract, like what even form is this in, what does it mean, and I'm about to explain that. So at the end of the day, once we're done deriving basically the change in C when we change some weight W, what we want out of this is a Jacobian or a gradient that we can feed to gradient descent to help find the minima of the cost. But the kind of thing that we want is something like this, where we have this vector, and each entry in this vector is how the cost changes with respect to some weight 1, and then some weight 2. And in our example with 5 weights, this weight matrix should be 5 members long, but I'll just put generally up to Wn. So in our case, that would be up to 5. So we want this. So we want this to output this. And now that we've taken the derivative, we just kind of want to double check that that is what we're getting. So let's see. So just to kind of understand a little better, and just looking at this, this is an error term. So W transpose X plus B, that's kind of our prediction. That's our prediction. That's our prediction A. That's the outcome, AL. And remember that we got rid of the max because we found it redundant. So that's prediction. So AL minus the corresponding real answer for that example is the error. So let's just put the error for example I as that. So let's rewrite this as the actually no. Let's keep that actually, and let's rewrite this over here. So in the case where W transpose X plus B is not less than 0, because in that case our resultant vector would just be 0, 0, 0. It would just be the 0 vector. And I know there's a bit of confusion saying 0 transpose, but just kind of disregard that and treat that as we're kind of transposing it back into a vector of zeros. So we've got that. So that's in the 0 case. That's easy. If W transpose X plus B is less than 0, then our gradients with respect to its weights are 0, because everything is 0. The activation is 0. There's no effect of the weights. It's all zeroed out. So we don't really need to worry about that. So let's worry about the non-zero case, because that's the hard part. So this part. So substituting this for the error term here, that's the error of I times X transpose. So that's a lot easier to look at, and don't forget about this. Alright, so this is a lot easier to think about. So you can think of the error term as how, obviously, incorrect the answer is. So looking at this X transpose and looking at this sum, so let's say that we only have one example, so M equals 1. So in this case where we only have one example, we can just get rid of this. And we can also get rid of this, but this will be 1 over 1, which is just 1. So we just have this. So in the case of one example, we just have our errors times our X transpose, which is just literally the inputs. So in our 5 input scenario, this is what it looks like. So when we multiply our error on our one example, what we're going to get, and I like to transpose this matrix just because our gradient that we put into gradient descent is usually shown as being vertical. So let's just kind of cheat and make this vertical. So x1, x2, x3, x4, x5, and then we multiply our e. So this error. So yeah, then we multiply this error by each thing, by each x, sorry. So this error will be the same, because this error is the same for every training example. Yes, so this I indexes training examples, but since we just have one training example, we can just do that. So this will be ex1, ex2, ex3, ex4, ex5. So this resultant vector here is how the cost changes with respect to our weights. No, our output cost is not. And the reason why we have a vector is because the whole cost function is just one big vector to scalar problem. Remember how we talked at the beginning how we get gradients in multivariable functions that take vectors to scalars? Well, that's exactly what happened. We put in our 5x's as our inputs, and then we put it through this neural network, and it spit out a singular cost, which is the mean squared error. The mean squared error. It's the mean of all the errors in something like this. So here is how the C changes to W1. Here is how C changes when W2. Here, C changes when it's W3. Here, just this is kind of a big moment for all of us. W4 and then W5. So exactly the cost is affected by this amount when you the cost, when you change W1 by a small amount, the corresponding change is this. So we kind of achieved our goal of knowing what happens when we change our weight. How does our cost function change? This is the answer. And the reason why gradient descent works, I'll go into shortly, but let's just see what happens when you have multiple training examples now. So when you have multiple training examples, what we do is we are now extending this vector. It's still a vector, but now we're taking sums. So let's see. So this took me a while to understand when I first got it, so let's see how well I can explain this. So looking at this, so let's just erase this and go back to our thing where we looked at this. So notice that this X transpose, which is our X1, X2, X3, X4, X5. So literally the error part, this is like all of those derivatives that we took, like all the product of all the chain rules. How we find in general the relationship we find is through the x's between the cost and the weights is through these x's. So that's interesting to note. But to find the real gradient, we have to multiply the error by each one, and we'll see why that kind of makes sense soon. But if we have multiple, so say we have n training examples, well m, obviously m training examples, this X transpose is always going to be this, but there's no index on this, so this will always be a vector, and we like to transpose this vector, so that's what I'm going to do. So just some x1, x2, ... x5. So this will stay the same each iteration, but this is going to change. Because each training example is going to have a different error depending on the answer or the inputs, all sorts of things. So it's going to have a different answer each time, a different error each time. But this stays the same, and we want one vector. So what we're going to get is we're going to get, for each derivative with respect to each weight, which is what each of these rows are, we're going to, for each, because of the summation, what we're basically going to be doing is this. We're going to be taking the errors of the first training example. Say we have 3 training examples. We're going to be taking the error of the first training example, multiplying by by x1, because we're going to have this x2 vector, and we're just going to do the exact same as before. So we're going to multiply this first error by x1, this first error by x2, this first error by x3, this first error by x4, this first error by x5, and that's just the same thing as saying e1 times xt, right? So then we're going to do that, and then we're going to do it again. So then we're going to plus e2 now, because now we're on to the second iteration. We're dealing with another error. This is a different number than this, because now this is a new training example. But then we're going to still multiply by the same the exact same X transpose part. Sorry. So you get the point. I won't fill this out totally, but we got that. So then on our third training example, you get the point. It's going to be the third error, and then it's going to be x1, and it's going to all the way down to e3, our third error with our x1. So we can just represent this in one kind of long vector, just saying e1 plus e2x1 plus e3x1, and then plus e2x2 plus e3x2, and then plus and then you get the point, e2x3 plus e3x3, and then that goes on and goes on, and then whatever. So, and then one last thing is we don't want to forget this 1 over m term. So basically for each of these rows, we take the average. So we don't want this going all over the place. We don't want a huge number here. So for each of these rows, we're going to take the average. So if there's 3 training examples, we're going to divide this by 3, and we're going to divide this by 3, and then we're going to divide this by 3, divide this by 3. So then after averaging all the things over the different training examples, the errors times the x components, what you'll get is just a general number that I can no longer really associate with xt with any of the values of x, but is now just an average. So let's just call this let's call it G1, G2, G3, G4, G5, that give a general idea of, per these weights and over M training examples, what's the general, when you tweak this weight 1 by some bit, what is kind of the ratio of the corresponding change in the cost function? That would be what G1 is. So it's actually quite beautiful what we get from this whole process. We get this long vector that's as long as how many weights are going into our node, into how adjusting each one of these weights affects the cost that comes out. So I just want to hit on one more thing, and that's this beautiful idea of gradient descent. Alright, similarly to what we did with the weight, now let's do the exact same thing. So let's see if we can find the derivative of the cost with respect to the bias now. It'll be quite similar. So we're going to do a similar thing where we segment this off into the intermediate function v. So we're going to say that y minus al is going to be equal to v. And using our same kind of chain rule idea to find the derivative of c with respect to b, we need to kind of chain it. So we can start with the c, but now we're going to be finding c with respect to v, and then we're going to be finding v with respect to al, and then we already know how al changes with respect to b, so that's not going to be that hard. So first we need to find this. So how to find how v changes with respect to al, well, that's just going to be minus al, and to find that other part of the chain rule here, multiply that by, minus 1. So how v changes with respect to al is going to be minus 1. So we got this one. So how v changes with respect to al equals minus 1. And then we need to multiply this by how al changes when we change b, but we already know that. So we need to multiply minus 1, so basically change in v when change l, and change in al when change b is equal to negative 1 times whatever our long and winding thing was. So it would be, so how al changes when we change b, it was either 0 or 1, right? Now let me just check. Yes. So it was how 0 or 1 changes when you change the thing. So it's going to be this. So it's going to be 0 if w transpose x plus b is obviously less than or equal to 0, and then 1, because when you're thinking about our w transpose x plus b, when you're taking the derivative of that, this is nothing to do with b, so that just cancels out, so then we just end up with a 1. So that's going to be 1 if w transpose x plus b is greater than 0. Okay, so that's decently easy. So if we multiply our minus 1 in, we'll get the exact same thing. So minus 1 times 0 is going to be 0, and then minus 1 times 1 is going to be minus 1. So not much of a change there. So we can actually simplify this into this. So the change in v when we change b, change in v when we change b is equal to this. So now that we've covered these last two derivatives, we only need to find how c changes when we change v. Alright, so now let's take the derivative of our cost function with respect to b. Just writing out our cost function over all the examples, and then b squared. Okay, so our first step is we can say that the derivative, the sum, is the same as the sum of the derivatives, so we can put all of that in. Don't forget our average, and then put this in here. Now we can kind of use the chain rule to split this v squared up into two functions. So to find the derivative of v squared, we can find derivative of v squared with respect to v, and then the derivative of v with respect to b. So we can just use that exact same philosophy. Can we do it around there without me redrawing things? Yeah, sure. So mi equals 1, and 1 over 2m, so now we're doing this. So how v squared changes with respect to v, that's just the power rule, so that's going to be 2v. So 1 over 2m equals mi equals 1, 2v, oh, that's a bad 2, 2v, and then this derivative thing here, multiplied by that. So we can take out this 2, and then we can put that over here, and then that obviously cancels out, so this all cancels out, so it becomes just a pure average, 1 over m, and then we're left with v times this derivative, so v times this derivative of how v changes when we change b. Great. So, now what? Well, how v changes when we change b, we already know that. We computed that over here. So what we can do is we can just substitute that. Similar to what we did before. -1, oopsies. Alright, so now we can put this v in, so v times 0 is going to be 0, and v times this is going to be negative v. And now we have to substitute negative v, doing the similar thing what we did before. So we have mi equals 1, and then we have this. So our 0 case is uninteresting, but what's our non-zero case here? I'm going to make some space to make this a little more clear. So 0 and then negative v. So if w transpose x plus b is greater than 0. So what is v? So our v we assign to be as this, right? So let's just substitute that. So it would be minus y minus al, and before we write, well, if w transpose x plus b is greater than 0. So before we solidify this, can we expand this further? Yes, we can. So this al is just the activation, so we're subtracting max of 0 and w transpose x plus b. But as we saw with the weights, we can do the exact same thing. Max 0 is completely redundant because the whole reason for this piecewise function is figuring out if w transpose x is greater or less than 0. So this whole max thing becomes redundant, because if it's on this opportunity, if it's chosen this path on the piecewise function, then obviously w transpose x is already bigger, so all we need to do is just get rid of that. And now just w transpose x plus b. So now we can distribute this negative, so it'll be negative y, and then plus all of this. And then we can just rearrange this to be nicer, so we can put our w transpose x plus b first, and then negate our y, and that's going to be our final thing. So it's going to be 0 if w transpose x is less than or equal to 0, and it'll be w transpose x plus b minus y, so that's the error term, if w transpose x is, is greater than 1. And then we can obviously put this sigma, and we can also put this mean. I didn't put the mean inside the piecewise function on the other one. I didn't really have an exact reason to, I just never kind of did that, so you're allowed to put the mean in as well as the thing. So why don't we do that as well, just to kind of get some practice looking at something like that. I'm going to erase this and go back up. So we can actually put all of this inside the piecewise, so 0 if blah blah, no, I'm going to write it out, I got to write it out. W transpose x is less than 0, but it's going to be 1 over m, going up to, summing up to m, of w transpose x plus b minus y, if w transpose x is greater than, did I write? It's greater than 0. Alright, so that's our final answer. Just noticing a few differences between the weights and the bias, is that with our weights we noticed that there was that x transpose term here. Now that's gone. Why was that? Because the derivative of AL was different. Because before the derivative of AL was x transpose, and that kind of carried over, and that became x transpose over there. So now we don't have that because the derivative of the bias with respect to the derivative of A transpose with the derivative of the activation with respect to B is going to be 1, so that's just going to be 1. So we're end up with just this. So this is a scalar, and that makes sense because in our simple neural network of just one neuron, there's only one bias to tweak, so that will be a scalar. So in a larger network where you have multiple layers, you'll have another bias for each layer, but that's still going to be kind of grouped as a single scalar that you kind of add to each layer. So the reason why this is going to become just a scalar, so we're going to what we're going to do is, before we had our gradient where each one we added the examples. If you have multiple examples, it's just going to be, so substituting this with our error term just to kind of get an idea. So error 1 times nothing, so it's just our error. So it's completely proportional to our error. So the error on 1 is the derivative, and then we just sum that by the error on 2. So if we have 3 training examples, then the derivative of how our entire cost changes when we change our bias will be the sum of the errors divided by 3. So that'll be kind of the average. So that's kind of something interesting to note, is that when we're finding how our cost changes with respect to our bias, it's completely proportional to the error on that layer. So we're going to kind of explore this concept of error when we're doing backpropagation, and we're going to kind of see, I guess, first why backpropagation works. But before that, I want to quickly talk about why we're computing all these derivatives. And I kind of hinted at it before, but we're going to kind of go a little more depth in gradient descent and the mathematical and graphical understanding of why gradient descent happened, and how gradient descent works. And I have quite kind of an interesting intuition that I'm looking forward to telling you guys, so stick around for that. Anyways, see you there. So let me just, if it's okay with you, let me just go back to the single training example scenario, so we don't have to really worry about the averages. The thing I'm about to tell you is completely applicable when we do those averages, but it's a little bit easier just to see an exact kind of thing being written out here. So let's try this again. Alright, so this is a 5-dimensional vector. And so let's think of this graphically. Let's take a smaller vector that we can actually kind of graph, so something 2-dimensional. Alright, so this is a network with 2 weights attached to it. So we can display this in a 3-dimensional graph. Alright, so I may make a little more space for this, because this is going to be pretty important. So we're going to be graphing now EI x1, EI x2. So these are how the cost changes with respect to 2 weights in a network that looks something like this here, with some weight 1, weight 2, and then activation. So that's what it would look like. So that's exactly what we're going to be doing. So this, theoretically, if you've ever been familiar with multivariable calculus or gradients, you've probably heard that the gradient of a function points in the direction of steepest ascent. And this gives us a really beautiful kind of intuition as to why this makes sense. So I kind of stumbled upon this, and I just kind of want to share it, and I think it makes quite a lot of intuitive sense. So let's amend this graph. So this is what value we give to our first weight, and this is the value we give to our second weight. And this is the cost. So when we're trying to minimize the cost, we're trying to get to the bottom of this, but let's not worry about that right now. So the cost is represented by some sort of 3D like shape here. I don't know what that is. It's like a curved blanket kind of shape. So there's a really nice intuitive way you can look at this vector and why it points in the direction of steepest ascent. But first of all, I just want to get the notation right here. So this is the gradient. So we just want to get used to gradients and the notation for gradients of the cost function with respect to the weights. So now we can start to get into why this points in the direction of steepest ascent and what this means for us trying to find the lowest cost. So we can see vectors in multiple different ways depending on what field of science or mathematics you're in. But something quite popular in physics and all the time in linear algebra is viewing vectors as lines, as arrows through space. Where, for example, here in x and y in the normal Cartesian plane, the direction of a vector can be described by its x-coordinates. So just like a point in a Cartesian plane and its y-coordinate. So given that, you can travel from the origin to this place. So we can do the exact same thing on our 2D plane created by our W1 and our W2 on this graph. So we can write something like this, where we have the component of W1 being graphed here, and the component of W2 being here. And these components that we get for our arrow are sourced from this vector. So the amount in the W1 direction is given by this, and the amount in the W2 direction is given by this. And there's just one more thing that I want to mention. Of course, this isn't really about mathematical rigor, because we're just trying to get a theoretical idea of why this makes sense, and not just like get calculations right. But there's just one more thing I want to mention, so you don't think I'm doing anything illegal. Vectors, as long as they're the same direction and the same length, you can move them anywhere in the plane. So they don't have, by default, they're attached to the origin, but you could write, if you did the exact same vector and you just moved it, if you just, I guess, kind of like shifted it, you can think of, that's completely fine. As long as it describes the same direction and movement. I guess same direction and length. Alright. So what happens when we think of this as a line in this plane? Of course, since this is 2, there's no way it can go up, because that would require a third coordinate, so it just acts in this area. So our idea is that this arrow on this plane points towards the direction where this cost ascends the most steeply. So say maybe in this direction it goes up very steeply, its slope, well, I guess it's a 2D slope, is very steep, so that means the steepest point in this direction. But why is that? Well, we can get quite a nice intuitive idea just by looking at this. So, one of the most important things we can notice, and one of the most important observations we can get from deriving all of this, is that the costs and how much tweaking some weight affects the overall cost is extremely dependent on the input associated with that weight. You see that these e's are all going to be the same. These e's only vary from training example to training example. They're the same for one training example, and we're only dealing with one training example, so this e is going to be some constant number. The thing that's going to change what makes some W1 affect the cost function more, so increase the ratio between this and this. So basically if we tweak this, this will be a bigger or smaller tweak, is the value of the input. So the value of the input is what decides the derivative, or how much changing a weight affects the cost. So if this input is very large, even a small change in this weight will cause a very large change in the overall cost. That can be a bad thing. So you can just change it a little bit and you get a huge change in the costs. As opposed to a smaller x, so let's say if x2 was something smaller, even maybe below 1, then any multiple of error against this will cause a much smaller change in this. So if we change, so you can almost think of it as changing W2 is less important than changing W1, because you get more bang for your buck if you're changing W1, because even small little changes to W1 will cause large decreases in cost. And this is really the heart of optimization with gradient descent, which I'll explain mathematically soon. But that's really the heart of it. We're trying to figure out how we can get the most bang for our buck by seeing the ones with the derivatives we can change the easiest with even small tweaks in W. often when training a neural network, these ones with very small inputs will just kind of be dead. Like, these nodes won't really learn. They might go up by some very small percentage, but the thing is they don't really have a reason to, because the whole way we evaluate how to increase some weights and decrease some weights is the overall cost of the network. And if changing some weight barely changes the output cost, we're not going to spend computational power changing that if we can just change this by the same amount and see like a 40 times difference in the cost function. So that's just something interesting to note. But that connects to what I'm meaning here. So if you imagine this as an arrow in space on this plane here, when x1 is big, that means that the error is magnified. So if x1 is big, even if the error is small, the error can be quite large. It can negatively affect the cost quite badly. So when you're creating this vector, what it's gonna do is it's gonna point in the direction of x1 and x2. So if x1 is very large, it's going to point more in the direction of x1. If x1 is very large, it's going to point more in the direction of w1. So if x1 is 100 and x2 is 10, then imagine what so let's say maybe the error is just 1 to keep it easy. So that means w1 will be 100. So that means, you know what that means. This is the w1x, so this is going to go on for a long time. But maybe if this is only 10, we're only going to see a very small difference here. So this is going to go on for a very long time, but there's only going to be a very slight change in this. Right? So that kind of gives you an idea why it points in the direction. It points in the direction of the weights that have the most impact, and therefore have the biggest cost, because their error is magnified by this x1. And for example, for this one, has a very small effect. It has a very, when you multiply the error by this, you get a much smaller effect on the overall cost. So it doesn't point in that direction as much, because that doesn't give you almost more bang for your buck, or that gives you, well, it's kind of a bad saying, but pointing in that direction wouldn't point you towards how to get to the steepest part of the cost as possible. Pointing to the steepest part of the cost as possible would be pointing in the direction of these magnified errors. So that's just kind of an intuitive understanding. But you might be asking, why do you want to know the direction of the highest cost? We want to be heading in the direction of the lowest cost. And the thing is that we can use the direction of the highest cost to find the direction of the lower cost. And the answer is, quite beautifully simple. It's just to take the negative of the gradient. And that instead of pointing in the direction where you get instead of pointing in the direction where you get the highest increase in cost, you get pointed in the direction where you get the lowest increase in cost. So you can slowly just kind of point in the direction of lowest cost as opposed to pointing in the direction of highest cost. And that gives you the foundation for the formula of gradient descent. So I'll slightly more in depth explain gradient descent in the next clip, but that's really the most important foundation, is that we can use this gradient to point in the direction on this graph, give you kind of the pointer towards the direction of steepest descent. That's a magical idea, and we're really going to use that whenever we use any sort of gradient descent. Every single optimization algorithm in machine learning uses this concept, whether it be something more new like Atom, or something that uses momentum, or it all uses this idea of taking advantage of this property that the gradient points in the direction of steepest descent. So I hope you're as excited as I am. I think it's quite a beautiful idea, and I'll delve into gradient descent for a couple minutes after this, so I'll see you at that. So now that you've calculated all these gradients, so you have this big long vector with respect to all your weights and your biases, so all in this vector. So you have your cost with respect to your first weight, and your cost with respect to your second weight, and then you have your cost with respect to your biases, and then you have all the way down to some final weight n or some final bias. It really doesn't matter which order you put them in this gradient. But then this gradient, you could say, is the gradient of the cost function with respect to w and b, or you can do it like this. There's multiple ways you can display this. I'm going to go with this. Okay, so that's your gradient that you calculate by doing that entire process of Jacobians and chain rules that we covered. And you combine it all in this nice pretty vector, so all the information you need is in here. So let's see how we can use this gradient, and kind of equipped with that that kind of graphical understanding that the gradient points in the direction of steepest ascent of our cost function. So something like this. So it points in the direction of how we can see the highest as quick as possible. It makes sense that our formula for gradient descent, so this is obviously, each one of these is some weight or some bias. So if we have all our weights and biases in one vector, so we can unroll something that we do if we want to quickly talk about how the code works in a neural network, is when we're about to do gradient descent, we unroll, we have all those weights matrices. What we do is we basically turn all those weight matrices into just one super combined long vector that's the exact same length as the gradient of the function. So we have all our weights and our biases in this vector, weights and biases, and then we have our gradients, and then those are the exact same length, so we can do element-wise operations on those. So the gradient descent algorithm uses this to its advantage. So the gradient descent algorithm is, so let's use capital theta to represent all weights and biases in our entire network. So so the new value, so basically what we're doing is, gradient descent is an iterative algorithm, and you probably know this, but I'm just kind of giving it in kind of the context of the neural network and the mathematics of it. So gradient descent is an iterative algorithm, so you don't just do it once and it finds a solution, unless it's an extremely easy problem. Or you might never find the solution, but the optimal, the highest, lowest possible error. What you do is you keep doing the algorithm over and over again until your cost gets lower and lower. And the reason why it does this is, so this is our, let's say we randomly assign our thetas and weights, our weights and biases at the beginning, before training anything, so our cost is going to be really high. So what we're going to do is we're going to do this. So we're going to take the same theta, and we're going to update it by an amount. So we're going to negative, and I'm going to use alpha. Let's draw a better alpha than that. Negative alpha, and then our gradient. So, all right. Just gonna get this out of the way. We know this is gradient descent. I'll keep this reminder for SGD. So this is our algorithm for gradient descent. It's deceptively simple, or maybe it's not deceptive, maybe it's just simple. But this is our algorithm for gradient descent. And we iterate this over and over again. So basically what we're doing here is we have all our weights and biases, and we update all these weights and biases by subtracting some, this is called a learning rate, some learning rate times our gradient. So this makes sense because we're basically taking the negative gradient, like this, ignoring this learning rate. We're taking the negative gradient, which now points in the direction of how we can decrease the cost as quickly as possible. And that's what we're looking for. We're looking for how we can adjust our weights and biases by the amount, by kind of push all our weights and biases in the direction of this arrow that points towards a direction of of lower cost, the steepest, quickest way to get to a lower cost. So we're kind of shifting this arrow by this. We're shifting our arrow, which might be pointing in some crazy direction, and we're kind of shifting it closer towards the right direction and closer towards a lower cost. So by shifting it by this way of getting the lower cost, we're just subtracting some element. Well, we're subtracting, basically the element-wise thing is some w, and then we subtract that by the derivative of cost with respect to w1, multiplied by some learning rate, and then we're doing w2 minus the learning rate. So it's an element-wise operation. And then we do our biases. And then we do all our weights. So that's basically what we're doing here, is we're subtracting the corresponding partial derivative from the weight. And this will slowly kind of nudge it towards the right direction, and hopefully getting closer and closer down to the solution. So this learning rate plays a critical role in how quickly you make these steps. You can think of it as steps down, how quickly you make these kind of edits to our weights and biases, and how big those edits are. Of course, these might point in the right direction, but if you make the learning rate too big, you might overstep, and then now you're actually in a place with worse cost, because obviously this points in the direction of the direction where we can lose the cost as quickly as possible. But of course these are just partial derivatives, so when you're thinking about derivatives in any way, you're talking about a very small change. So even though this might say, oh, this direction is good, that's really measuring, oh, this measurement is good if we move like an infinitesimally small amount in that direction, because this is still a partial derivative. It's not. It's a very small number. So multiplying this very small number by a lot could be overstepping way too much, and then you might be way past where that move was helpful. So now you might be in a place of actually worse cost. Furthermore, if you take a learning rate that's way too small, you will probably find the answer, but it might take just way too long, because all our steps and edits will be just very, very tiny. So finding that learning rate is called a hyperparameter, because well, there are algorithms that are coming more and more that can help find the best learning rate, and then obviously there's just brute force algorithms where you just run the entire program on different learning rates, and then just kind of like center it, you just kind of close in on the best learning rate with the lowest cost. But there's different ways to find that, but that's a hyperparameter, and that often the machine learning engineer or researcher has to kind of figure that out themselves in part, a little bit at least. So yes, so this is that. So in the classic sense, in the way that gradient descent is kind of first taught, is that we do gradient descent over our entire, so we have a training batch of maybe X examples, so let's say, well, M examples. Let's say M equals 100. So basically what you do is you calculate the average gradient over all these 100, so you calculate this, and then that, and then that. So then you have all these averages, and then you get a single kind of average gradient that's taken the average of all 100 of those examples, kind of in that way we saw before, where it's like EIX1 plus E2X1, and like in that way, but for 100 training examples. And then when you're thinking 1,000 training examples, and you're thinking more and more and more and more and more, probably not that much, but that gets computationally expensive, because now you're basically running the algorithm and computing the partial derivatives with respect to every single training example, and that can just get to be a lot when you're dealing with that much data. So what probably the leading tactic now is, although people might not be explicitly using stochastic gradient descent, or SGD, as I put over here, and people might be using slightly more sophisticated algorithms, the idea of batching up your training set into multiple smaller batches. So we can turn this X, so of maybe, let's say, 100,000, that's 1 million, but that works as well. So let's say we have 1 million training examples, which is definitely totally plausible for any data set. Many data sets have much more than that. So we have 1 million training examples. So let's say we can batch this into maybe batches of maybe 120. Why not? So 120, so we can batch this into groups, so however 1 million divided by 120, we'll have that many batches. So we'll have each of these batches, so we can kind of segregate this as into, I'm not sure there's a specialized notation for it. It really doesn't matter for our purposes. Let's say there's that's our first batch, and then we have some second batch. So each of these is 120 training examples, just each of these. So we have 1 million divided by 120 of these training examples. Actually, hey Google, What's 1 million divided by 120?
The answer is approximately 8,333.333333.
Alright, so that many batches. We have about that many batches of these 120. So what we're going to do is we're going to do stochastic gradient descent on this batch. And then we're going to do stochastic gradient descent on this batch. And then we're going to do stochastic gradient descent on the next batch, and on the next batch, and on the next batch. And what we're going to do is we're going to take, remember how we would have to calculate the partial derivatives with respect to all 1 million of our training examples just to take one step of gradient descent. Because we would have to create this 1 million long E1 x1 plus E2 x1 plus all the way down to E1 million x1, and then we would take the average over 1 million for that row, and then we would do the ones with, so if you have tons of weights and tons of training examples, this gets this just totally gets completely unreasonable when you're getting to larger sets of data and larger amounts of parameters. So what you have to start doing is you have to kind of start, so obviously this is the most perfect way to do gradient descent. You can think like, this is the most mathematically perfect and rigorous ways that we kind of check every single training example, and we take it, and we kind of take every training example into account when making our decision to, okay, what direction should we go? But mini batch is another word for it, but stochastic gradient descent says this is good enough. So what we're going to do is, instead of taking 1 million training examples to take one step, we're going to take 120 training examples and take one step based on that. So now we'll only have 120 training examples in our batch, and then we'll do that, and we'll do that, and we'll do that. And usually it's nearly the same as just doing, completely vanilla, taking everything perfect, kind of for the perfectionist approach. Now we're kind of just saying, okay, let's hope that these 120 examples represent the entire training set quite well. And that's why obviously we need to shuffle our data before doing anything on it, because of course if this is ordered data where you have some A, and you have right answers all here, then this is going to be all some answer. So we need to shuffle very well before, and making sure that we don't have any preconceived kind of unknown biases in our sorting of the training data. So in this perfectly shuffled, or as close to perfectly randomized shuffling as possible, we're going to cut this 1 million to 8,333 different batches, and then run our normal gradient descent on these smaller training sets, taking one step each time. So now we can actually take 8,333 steps, where before we could only take one. Because before we would have to compute this entire 1 million and then take one step. Now we can take one step after computing each batch. So that means we'll be able to take 8,333. So we're able to take 8,332 more steps by using stochastic gradient descent, which, obviously this becomes unreasonable very quickly. So just some kind of information on the naming of these. It can be a bit confusing because there's a version of stochastic gradient descent that is originally just called stochastic gradient descent that actually does this, but does batches of size 1. So we're actually taking one training example into account at each time. So our line to the lowest cost, if you can think about it as this kind of contour plot, and then this is kind of our lowest cost. If we're doing real stochastic gradient descent, or kind of like one example learning, or we're just doing gradient descent on one example is going to be much less representative of 1 million examples than even 120 will be. So our path from, if you can think about this contour plot as representing the costs, will kind of be much more jagged, because we'll be kind of pushed this way by one example, push this one, but in general, after many different times, we should be able to get there. Our stochastic gradient descent, which I think the real kind of rigorous term is mini batch gradient descent, which makes it quite obvious, but it can be quite but usually when people talk about stochastic gradient descent, they're talking about this mini batch using segmenting up into batches. So if we use this version, then we get this kind of maybe slightly more jagged line, but we get there fast. If we did the entire perfectionist kind of view, we would get there in kind of the most prettiest line possible, but it would take years. Well, not years, but it would take an insane amount of time. So that's just a super quick rundown on gradient descent. Hopefully you're already familiar with that, but just kind of closing this picture of our simple neural network with 5 inputs, and how we can find the optimal parameters and bias settings for that to lower the cost using stochastic gradient descent. So next up, I'll try to explain how we can get from this x1, x2, blah 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 single node system to a system with many more nodes, and seeing how that works and how we can do similar things to what we did with one node with multiple nodes. So I'll see you there. Alright, so now that we've finished talking about the derivatives of the weights and the biases in a small neural network, let's see how this works with slightly larger networks. So let's take something where we have 3 inputs, and then these go to some 3 nodes. So let's make a 3-layer neural network. And this goes to some 4 nodes. And this goes to 1 node. And this gets computed some sort of cost. So we have 3 layers, 1, 2, 3. And then we have some 3 weights matrices, weight 1, weight 2, and weight 3. So how would we calculate each one of these derivatives of the weights and the biases? But, you know, if we manage to do the weights, the biases come pretty easily. With the cost with respect to the biases and the weights. Well, the thing that I kind of want to show is that it's pretty hard to do this when we're thinking about going forward in the way that we were kind of thinking about before. Yeah, so it's quite cumbersome, and let's see why that is. So theoretically, if we're just kind of using the simpler kind of chain rule intuition, if we wanted to find maybe the entire cost with respect to the first set of weights, we would do something like, so we want to find how the cost changes when we change the first set of weights. So then we would find how, we would start from here somewhere, and we would see how maybe the first layer of activations, so this is the first layer of activations, this is the second layer of activations, and this is the third activation. So we would probably see how the first layer of activation changes when we change the first weights, and then we'd probably see maybe how the second layer of activations changes when we change the first layer of activations, and then see how the third layer changes when we change the second layer, and then see how the cost changes when we change the third layer. Likewise, we could see something like, but then if we wanted to find the weights too, then we would have to change to how we would be doing this. So then we would start at how maybe A2 changes when we change the second weights, and then we would see how maybe the third layer acts to change when we change the second layer, and then how the cost changes when we change this third layer here. But there's kind of a few problems of how kind of cumbersome this is of kind of going back and forth, because you're going to be computing derivatives multiple times, because computationally these will still be different actual numbers, so you're going to be multiplying different numbers with respect to the cost, and you're also going to be, for example here, even though you have less derivatives to deal with when you've kind of trying to compute the weights farther along the network, the actual numerical numbers of the derivative with respect with C with respect to W2 are dependent on what A1 is, which is dependent on what W1 is. So then you're going to have to kind of calculate how does this affect W2, which is also kind of a pain. So you're no longer really taking the derivative. You have to do some more chain rule magic to kind of see how these numbers affect W2, because remember, in our kind of W transpose X kind of derivations, we see that in any layer the weights are kind of parameterized, or the weights are proportional and multiplied by the inputs. So we're going to try to figure out where these inputs come from. That's going to come from there. So it's just going to be kind of a mess in general when we're trying to compute the derivatives forward. It's possible, but it's not done. It's not really done that often. So instead, we use something called backpropagation, which is probably the most famous algorithm in machine learning, is backpropagation and how we go backwards from the cost through the network to calculate the derivatives with respect to each of our weights. And the reason why this works a little better is that once we've calculated everything, we get our final cost. And we can just kind of index one by one and see how this impacts our cost. And then we can go just one step further and see how that impacts this and how that impacts our cost. And by going backwards, we save a lot of efficiency, and we don't really need to go back and forth because we can just, as we kind of stroll through the network backwards, we can kind of accumulate oh, this changes that, so that means when we go to here, that'll change that, and that'll change that, and it'll go to here, and we kind of accumulate our way through the network. We can just kind of, through a single pass backwards through the network, we can calculate all the derivatives we need because we can just kind of accumulate them in these error terms. So we're going to be introducing this kind of concept of the error of one node. So some error of some node in layer L and some node J in some layer L, and how we can kind of calculate basically from this one node how much error is it causing in the cost function, and how we can use that to parameterize and kind of help solve for the optimal amounts on our weights and our biases in a much larger network, and kind of switching pace from this forward idea to this backward idea of backpropagation. So next up, we're going to talk about these four critical equations, and this idea of four critical equations comes from a man named Michael Nielsen. Michael Nielsen's book, he put it quite succinctly with these four fundamental equations of backpropagation, which I'll go through, and then I'll kind of extend on how these work with Jacobians and matrices near the end of this lecture. So let's jump into those four equations and help derive them. And I won't show super tough like numerical proofs for them, but I'll hope to give some intuition as to why they make sense just by using the chain rule and kind of filling in the gaps. So yeah, so be excited for this kind of last part where we look at the laws of backpropagation and truly understand how we backpropagate through a network and how we decide exactly how each of the weights affect the cost and how we can put those into this final gradient. So now we know our motivation for backpropagation. We're trying to find this gradient of every weight and bias with respect to the cost. So now we're kind of doing backpropagation as how do we get there? So we know why, but how do we get there? So I'll see you in the next part when we start talking about the rules of backpropagation. Now that we're talking about backpropagation, it's really important to mention this concept of the error of a single node. So let's take a look at some neural network. Alright, so we have maybe 3 inputs. And this all go into there. Alright, so the error of a node is choosing some node. Let's say this one. So this is in the A1 layer. So let's kind of build the graph for this one. So choosing this node, which could be represented as W transpose X plus B, like all nodes. So let's say maybe this node. So that would be A 1, 2 equals this. So this specific node here, if we were to add if we were to change this quality of this node by a little bit, how would the overall cost change? There's just one more kind of specificity here. We're not actually talking about A. We're not actually talking about adding a small quantity to the entire value of A itself. For just mathematical reasons, you'll get a similar answer using this method, but what we're doing is we're actually adding a small change in the z of this. So really, we're talking about adding a small change in the z1, 2 value of this node. So basically, the activation of this node before it goes through the activation function. So the z1, 2 of this node. So if we add some small quantity, to this node, how will the overall cost function change? So that's the idea of an error of a node. So mathematically we can describe this as the error of a node may be generally a node, the error of a node, I guess I'm trying to find a good way to say this, the error of a node can be described with this symbol with L and J. So the layer L, in some layer L, the jth neuron layer L. So in our situation, it'd be the error would be 1 and 2, is described by the change in the cost function when we change z of L, J. So in our situation, the error of this node 1, 2 equals how the cost changes when we change z 1, 2 of this node. So that's just an important thing to keep in mind. And I guess one last question is why exactly this makes sense and why we call this the error of a node. And just think about it like this: if this error derivative c with respect to z L J is close to 0, that means changing the value of z has little effect on the final cost. If alternatively this has quite a large value, changing the value of this creates a large change in the cost. So kind of going back to this bang for your buck idea, if you wanted to decrease the cost, you would want to take the negative of the derivative of this larger cost, and that would actually reduce the cost by quite a bit. Or if you were somehow able to kind of alter, if we know that altering this node by a little bit can decrease the cost quite a lot, we can say that this node is actually causing a lot of error, because this node is kind of magnifies anything that multiplies into it because it's such a large derivative value. It changes the cost function so much. Similar to how we were looking at the gradients and how they point in the direction of steepest descent. This is kind of a similar thing. But now we have these nodes with large derivatives kind of magnifying any error that we have. So we can actually call this really the error of a node, or kind of a more specific way to call it would be the impact of a node on the cost, or something like that. But we can really just shorten this to the error of the node, because we can see from this total error C how much of this error is being caused by each of the nodes. So maybe all, you can almost imagine like a pie chart of C, and how much of each of the, how many ever parameters there are of this cost is being caused by one of the nodes. So that's the idea of an error of a node, and this will be extremely important in all 4 of our equations regarding backpropagation and how we compute the derivatives with respect to the weights, because obviously the weights and the nodes are very unconnected. So this idea of the error of the node can help us derive the weights and the biases. So let's go right into the first rule and see how we can figure out the intuition of that. The first rule is actually quite simple, so we should have kind of a nice, easy start. So let's go to that. The reason why we're outlining these four central equations to backpropagation is that they basically make up the whole of backpropagation. Like once we know these four equations, the steps of backpropagation will become quite clear. So using this intuition of some node's error, so some node L, some node J in layer L is equal to how the cost changes when we change this node's Z value, so Z Lj. Let's see if we can find the cost or the error of a node that is in the last layer of its network. So it's getting directly compared to with our real answer y. So for example, in our neural network like this, where we have our final answer here, this final activation AL, and AL is actually just equal to the sigmoid of ZL. How does this overall cost, which is kind of, there's obviously more different types of variation on it, but some kind of version of the real answer minus AL, maybe squared or something, that cost, how does that cost change when we change Z? So what we're trying to find is how does that cost change when we change the Z of the last layer? So there might be multiple in here, but any node in the last layer, how does the cost change when you change the error of the last node? Change the last node. So let's try to figure this out. So we can kind of intuit that we're looking for capital L here, so capital L being like the last layer of our network and some J. And this can equal, well, we're still going to have to use a very small chain rule thing because the whole definition that we created of the error of a node deals with the cost with respect to some sort of Z value. And when you're at the end of a network, you're comparing the real answer with your A value, not your Z value. So the A value is basically just a Z going through a sigmoid function, so we still need to compute, we're computing some sort of with respect to Z terms, so we have to compute some respect to A term first. So to see how our cost changes when we change ALJ, so some activation node in the final layer, multiplied by how this activation node in the final layer changes with Z. Alright. So simply enough, this will just be the derivative of the activation function. So I won't explicitly put the derivative here. It could be ReLU, it could be sigmoid, but it'll be something, and it'll be the derivative. It'll be the derivative of that function with respect to ZLJ. And then we're going to multiply this by whatever cost function you're choosing, maybe MSE or something like that, where you're comparing the real answer against the fake answer and squaring it or something like that. So whatever that is, we're taking it with respect to our output AL. So that's going to be the derivative there. So it's basically going to be the derivative of our cost function with respect to AL, our final activation output. So I'm just going to keep that there since there's really no need to compute that. We already kind of did compute that with our smaller neural network, so it would be something like that. And whatever this ends up being is our LJ. So this, as you notice, is actually a component-wise kind of equation for this error of the last node, because we're looking at specific nodes J in the ending layer, but really for backpropagation we want to see kind of more matrix-based notation, so we want to be dealing with the entire layer. So let's exactly do that. So let's find now the error of every node. So now we're going to get a vector of errors. So something like, so all we need is the layer. So we're just looking for some errors of the layer, and each of these is going to be the error of each node in that layer. We're looking for this vector now. So now we're looking for this. It's going to equal So the thing is, if we put in this cost, if we're taking the derivative of this cost with respect to all of the nodes in the last layer of last layer AL, we're taking the partial derivatives of the cost with respect to all the different AL nodes. So what we're doing is we're actually getting the gradient of the cost with respect to A. Before we were looking for the gradient of the cost with respect to W and B when we were doing back propagation, or not really back propagation, but when we were trying to derive the cost with respect to the weights and the biases. But now we're just doing it with respect to all the values in AL. So what we can do is we can actually take this this derivative and kind of display it notationally as a gradient, because that's exactly what it is. And then we can multiply this again by the same thing. The only difference here is we're going to just put L here. So you can think of that as an element-wise, we're basically finding the derivative of whatever our activation function is, and then we're plugging each element from our z vector, which is again just going to be a vector of all the z values of the nodes in our final activation layer, and we're just going to be element-wise be applying this derivative of our activation to like z1, and then derivative of our activation to z2, and then you get the program. So it's all going to be kind of element-wise operations here. This is going to be an element-wise multiplication between each item in the gradient and each item in whatever this vector ends up being, which is going to be this thing, and that's going to be our vector of errors that we're going to use. So that's the first equation in our matrix form. We're going to be showing the next three equations all in this matrix form, so it's all going to be associated to finding the error of some layer, or later on the last two, the weights of some layer and the bias of some layer using these errors of layers. So let's just dive into that yeah, there's not much else to go on about this one, so let's go into the second equation, which is the error of any node. So if we have so I'll explain the significance of that in the next clip. Bye. So now that we know how to find the error of the nodes in the final layer of our network, how can we use this to find the error of any node in our network? Well, this formula tells us how, if we have some layers of our neural network, if we know the errors of the nodes in layer L plus 1, we can use these to derive the errors in layer L. So this is basically what it's telling us. So using this formula, we can backpropagate through a network and kind of cumulatively find the errors with respect to each of the nodes. But if we know this one, we know this one. If we know this one, then we know this one. And this formula tells us how we know that. So this formula tells us that if we have the weights matrix of L plus 1, so that's a weight matrix that connects these two layers, L plus 1 and L. Remember that the weights matrix syntax is that the superscript is the layer it's going into. So if it's going to L plus 1, that means it's coming from L. So the weights matrix that tells us what all these weights are. If we transpose that weights matrix, so if we flip it, and multiply it by the vector of errors of L plus 1, so the three errors associated with these three nodes, and multiply that element-wise, so we can show that as that. If we multiply that element-wise by the activations of the z's in this layer, so the vector of z's in this layer, so the ones that haven't been touched by the activations yet, then we can get the errors. So what will outcome is a vector of arrows which has the same amount of entries as the amount of nodes in this layer, and each entry in this kind of error of L matrix vector is the error associated with each node. So let's explore kind of two reasons why this works out. One is kind of super intuitive, not super intuitive in the sense that this is the one I've seen before been used. To me, it doesn't really fill all the gaps in. But then I have another thing that I haven't seen shown before that really made sense to me when I first kind of figured it out. So let's start with the first intuition. So when we multiply the errors of a layer that's in front of the, if we know the errors of layer L plus 1, we can think about it as when we multiply by the transpose of the weights matrix that connects these two layers. We can almost think of it as, instead of, when we're feeding forward through a network, we're multiplying this, and we're multiplying in each node, in each layer, we're multiplying the weights by the inputs to the nodes, and then kind of going forward. Well, now when we're multiplying the transpose of the weights matrix, we can almost think of it as going in reverse. And going in reverse from these nodes and back propagating the error to the layer before it. And if you look at the dimensions, it makes sense. And if you look at how a weights matrix, just kind of some hints on the intuition here, the weights matrix, the columns are the K. So you remember when we saw this J, K, L? So the K is the columns that it came from, and the J is the columns that it's going into. Well, the columns are the K, so the columns are where it's the columns are where it came from. So if we flip this and we get this thing where we now have the J and the K, now the columns are where it's going into. So when you're thinking about multiplying that, you're almost kind of reversing the process of feed forward. So now you're kind of back propagating these errors through your network to the layer before them and seeing, and that's basically what intuitively what we're trying to do is we're trying to find the errors of this layer by kind of accumulating the errors of this layer and seeing how these ones kind of go, how these ones affect these ones, and then we can find this one. And then we multiply this activation of the ZL, because remember how the error is defined as how the cost changes with respect to the Z. And then if you're thinking chain rule wise, we can't just go straight to the AL, so we have to multiply by the ZL there. But something that makes a lot more sense to me is this kind of chain rule intuition. This way you can fill the gaps of the chain rule in a way that makes sense. So let's start off with an example and see if we can see if by trying to find the error in our example we get something that completely matches this formula. So let's take an example, and I'm going to use the same notation that I talked about at the beginning of this lecture, where we're going to represent the entire layers of a neural network just in this kind of horizontal way. So let's say we have some weights matrix 1, so I'm going to use actual numbers here, not variables, and some vector A0 of inputs, so that could be said to be x, but I'm going to say A0. So this is the first layer in the entire neural network, and then plus the biases, which is also a vector. So that's a matrix, that's a vector, and that's a vector. This is representing an entire layer. And now we can go to the second layer and see how we're using a new weights matrix, or we're multiplying by the outputs of this layer of nodes, so A1, and then we're adding a new bias vector. So here we have two layers of a network kind of represented in this way. So how can we try to find the error of the layers, the error of the nodes in layer 1? That's going to be our goal, to see if we can find the errors of all the nodes in this layer. And obviously, we're still keeping in mind that it's the Z we're looking for. So Z1, we're trying to find this. So using that definition of the error, how can we kind of derive from the chain rule what's missing? And you'll see what I mean by that. So what we're trying to find is some change in the cost with respect to Z1. Right, so this is Z1, this is Z2. So, alright. So, given the error of this, so say we're given the error of the layer in front of it, because we're back propagating. So say we somehow already calculated the errors of this layer. So we have the change in C with respect to Z2. That looks like ZZ. Z2. Somehow we have that. How can we get from this, you know how when you're doing the chain rule you have some F and how that changes with respect to X, but then you can split that up into how F changes with respect to U and how U changes with respect to X, and then you can kind of cancel those out. You can think about canceling those out and getting how F changes with respect to X. Now we can kind of do the same thing. So now we're seeing that we have the cost in the numerator, in the numerator. How can we get z1 somewhere in the denominator so they can all cross out and we end up with this? So that's kind of what we're doing. We're kind of doing some detective work in how can we fill these blanks? How can we connect z2? How can we connect from how the cost changes in z2, how the cost changes when we change z2, to how the cost changes when we change z1? So we're going to try to think about what change in z2 affects some sort of change so that we can kind of go backwards in our network. The best kind of link towards this, and the kind of most obvious link, is, so we want to match this, right? We want to match these numerator and denominator so they can kind of cancel out. And then we want to see how z2 changes the entirety, how z2 changes when we change a1. Because a1 connects us back to here. So we're trying to find a way to kind of make these kind of chains, links in our chain, so that we can kind of get back to here. So what we're trying to do is we're going to see how the cost changes with respect to z2, so that's the error we're given. So this is equivalent to the error term of layer 2. So we're given that. And then we multiply with how z changes with respect to a, so we're kind of chaining our way back. And then now we're kind of back here. So now we can see how a1 changes with respect to z1. And now we're here. You see that we can cancel these out, and we're left with the change in c with respect to the change in z1. But let's not cancel that out just yet. So this is, let me just kind of write this here. This is the error in layer 1. So what are these? And what happens when you multiply these out? Well, let's make some space. So I'm trying to find a good place where I can make some space here. Everything here is kind of important, so it's tough. I'm going to get rid of these. I'm going to kind of trust that you know these are the error terms. I'll rewrite them right above. So that's error 1, error 2. So let's see if I can make some space down here. So, alright, so what are these terms? So we know that this is the error term of 2 that we're given. It's a bit small. 2. So we know we're given that. So we're always multiplying these, right? It's a chain rule operation. So how does z2 change in terms of a1? Well, this is the only thing that you kind of need some mathematical knowledge that I didn't really supply in this course. But how z2 changes with respect to a1. So how z2 changes with respect to a1. So how does this entire thing here, this interior, change with respect to a1? So b2 is obviously out of the picture because it's addition and that has nothing to do with it, so that becomes 0. So the thing connected to it is w2, which is a matrix. This is a matrix vector product. We're multiplying a matrix by a vector. And I don't really have the time to prove this, but when you're taking a matrix vector product or a matrix product where you have some matrix A and some vector B, the derivative of the entire, the derivative of the vector B with respect to, the derivative of the vector, the derivative of the matrix vector product AB with respect to with respect to A1, which would be the vector B, is going to be A transpose. I really don't even have much good intuition as to why this works. There's honestly not even that much information online, but there are a few proofs out there if you look for them. I found a few good articles that I'll try to link in the description as to why this makes sense. But let's just take it for granted and say that makes sense. I do this rarely, but we're really focused on neural networks here. But let's just take that as a given that the derivative of matrix vector product with respect to the vector is the matrix transposed. So we can say that since this is a matrix vector product, and we're taking the derivative with respect to the vector A1, our derivative is going to be W2 transpose. Okay. And then this A1 over Z1 is pretty easy. It's just how this entire function a1 changes when we change z1. So that's obviously a chain rule to do with the activation function. So that's going to be how a1 changes with respect to z1 is just going to be the derivative of our activation function, whatever that is, with our derivative of that with our z1 inside there. So that's what we're doing. We're multiplying these three elements here. We're multiplying, and let's make some space for this. And I think now we don't need this graph anymore. It's pretty messy anyways.